Some places seem to ask questions simply by existing. A fortress standing where no army should have reached. A city carved into solid rock. A temple aligned with the sky so precisely that modern instruments continue to verify its accuracy. None of these places are legends. They are real, measurable, and still standing today. Yet the closer we examine them, the more difficult they become to explain. Every discovery adds another layer instead of removing one. Every answer exposes another mystery waiting beneath it. Across the ancient world, countless structures continue to challenge what we think early civilizations could achieve. And perhaps the greatest surprise is this. After centuries of exploration, we may still be standing at the very beginning of understanding the past. Southern Spain, near the modern city of Linares, beneath rolling hills rich in metal ore, lie the ruins of Castulo. For more than 2,000 years, this city controlled one of the richest silver-producing regions in the ancient Mediterranean. Yet the greatest mystery is not the wealth it generated, but how ancient engineers repeatedly found, extracted, processed, and distributed enormous quantities of silver using technologies that modern archaeology still struggles to fully explain. Although Castulo had been known through ancient Roman texts for centuries, systematic archaeological excavations accelerated during the 20th and 21st centuries, revealing monumental buildings, advanced urban infrastructure, mining connections, and evidence of extensive trade networks that once linked southern Iberia to much of the Mediterranean world. Everything about Castulo begins with silver, as the city occupied a strategic position near the Sierra Morena mining district, one of the richest metallogenic regions in Europe. Geological studies indicate that these mountains contain extensive deposits of silver-bearing lead ores, some of which have been exploited since prehistoric times. And during the Iberian, Carthaginian, and Roman periods, the region became one of the most important sources of precious metals in the Western Mediterranean. What remains difficult to explain is not that silver existed, but how ancient miners repeatedly located economically valuable ore bodies with remarkable efficiency. Modern mining companies employ seismic surveys, geochemical analysis, airborne magnetic mapping, satellite imagery, and three-dimensional geological modeling. While ancient prospectors possessed none of these technologies, yet archaeological evidence suggests they repeatedly identified productive veins buried within complex geological formations. Some mining galleries discovered throughout the Sierra Morena region follow ore-bearing structures with surprising accuracy, and in several cases, excavated tunnels maintain alignment with mineralized zones over considerable distances, raising an uncomfortable question for modern geologists. How did ancient miners know where to dig? One possibility is that generations of miners accumulated empirical geological knowledge so sophisticated that it effectively functioned as a practical science, using indicators such as surface discolorations, vegetation anomalies, exposed mineral fragments, groundwater chemistry, and subtle rock formations. However, archaeology has not yet reconstructed the complete decision-making process behind their success, and the mystery deepens when production scale is considered. Roman records suggest that Iberian mines generated enormous quantities of silver and lead, with some historians estimating that Spanish mining districts contributed significantly to Rome's monetary system, while lead isotope studies have traced Iberian metals to locations across Europe and the Mediterranean, demonstrating the vast reach of these operations. The challenge remains understanding how a society lacking modern geological instruments could maintain resource extraction on such a scale for centuries. Finding silver was only the beginning, as once ore emerged from the ground, it had to be transported, processed, smelted, refined, weighed, secured, and distributed across hundreds or even thousands of kilometers. Archaeological evidence reveals that Castulo was strategically positioned along major communication corridors, connecting inland mining regions with Mediterranean trade routes, allowing movement of resources toward coastal ports and commercial centers. Today, economists describe such systems as integrated supply chains, yet ancient societies were not supposed to possess the organizational capacity associated with modern industrial logistics. Despite this, evidence from Castulo suggests a remarkably coordinated operation involving miners, metallurgists, merchants, administrators, laborers, and transport specialists. Comparisons with modern mining operations reveal an important similarity. The greatest challenge is often not extraction itself, but coordination, as ore has little value unless every stage of the system functions efficiently. The remarkable fact is that much of the administrative knowledge required to sustain this network has disappeared as archaeologists can identify infrastructure, measure production capacity, and reconstruct trade routes, but cannot fully explain the management system that held everything together. Extracting silver from ore is far more complicated than finding it, as silver in Iberian deposits commonly occurs alongside lead minerals such as galena, requiring multiple stages of processing including crushing, smelting, and cupellation. Cupellation is particularly fascinating as in this process, lead is heated under controlled conditions until oxidation separates it from silver, and even slight mistakes in temperature control can reduce efficiency dramatically. Modern metallurgical laboratories achieve precision using thermometers and analytical instruments, while ancient metallurgists possessed neither. Yet archaeological remains from Iberian and Roman mining districts suggest that craftsmen consistently achieved results sufficient to support large-scale silver production with their furnaces, fuel management systems, airflow controls, and practical understanding of metallurgy, demonstrating technical capabilities that continue to impress modern researchers. The unanswered question is how such expertise was developed and transmitted, as no surviving technical manual fully explains the accumulated knowledge behind these processes. The furnaces survive, the silver survives, but the instructions do not. One of Castulo's most famous discoveries is the Lion Mosaic, which at first glance appears to be a beautiful example of Roman decorative art. But closer examination reveals something more intriguing. The mosaic consists of thousands of precisely shaped tesserae arranged into complex geometric patterns, and maintaining proportional accuracy across a large surface requires planning, measurement, and geometric control. Modern surveyors use lasers and digital instruments to maintain alignment, while ancient artisans relied on cords, rulers, plumb lines, and techniques that are only partially understood. Researchers studying Roman mosaics frequently observe that minor errors introduced at the beginning of a design should accumulate over distance. Yet many ancient mosaics maintain astonishing consistency, suggesting that craftsmen possess practical mathematical methods that were highly effective despite technological limitations. The Lion Mosaic is therefore not merely artwork, but may represent a visible trace of a sophisticated measurement system whose details have largely vanished. Most ancient cities evolved chaotically, with buildings collapsing, streets shifting, political powers changing, and urban layouts becoming distorted over time. Yet Castulo presents a different pattern. Archaeological excavations indicate that key routes and strategic zones remained important through multiple cultural transitions, including Iberian, Carthaginian, Roman, and Visigothic occupations. This continuity suggests that generations of builders repeatedly recognized the same advantages in terrain, drainage, transportation, and defense. Modern urban planners use topographic maps, hydrological models, and geographic information systems to identify optimal locations, While ancient planners relied on observation and accumulated experience, yet many of their decisions proved remarkably durable. The persistence of urban organization across centuries hints at a knowledge system that archaeology can observe indirectly but cannot fully reconstruct. No city survives without water, and southern Spain experiences periods of drought, seasonal variation, and challenging climatic conditions, meaning that maintaining a large urban population required careful management of water resources. Excavations have identified evidence of reservoirs, drainage systems, and hydraulic infrastructure associated with Castulo. Yet, what remains uncertain is how engineers calculated capacity requirements and long-term sustainability. Today, hydraulic engineers model water systems using advanced software and climate data, while ancient engineers relied entirely on observation and experience. And their success demonstrates practical knowledge that may have been far more sophisticated than surviving texts suggest. Along the rugged Mediterranean coast of southwestern Turkey, where mountains plunge directly into the sea, the ruins of forgotten cities lie scattered among pine forests and limestone cliffs. At first glance, Beydaglari Coastal National Park appears to be a landscape of natural beauty, but hidden within it are ancient harbours, stone cities, tombs carved into mountainsides, and engineering achievements that continue to challenge modern understanding. Although many ruins were known locally for centuries, systematic archaeological investigations intensified during the 19th and 20th centuries, and researchers soon realized that this coastline had once been one of the most strategically important regions of the ancient Lycian world. What they discovered was not merely a collection of ruins, but evidence of sophisticated engineering systems whose full technological foundations remain uncertain today. One of the first puzzles confronting archaeologists is geographical rather than architectural, as the ancient inhabitants of Lycia developed thriving urban centres in an environment that seems fundamentally hostile to large-scale construction. The Beydaglari mountain range rises sharply from the Mediterranean, creating steep slopes, unstable terrain, and limited agricultural land. Yet cities such as Phaselis and Olympus flourished here for centuries. Modern urban planners would immediately identify serious challenges, since transporting construction materials through mountainous terrain dramatically increases labour costs. Establishing reliable water supplies requires extensive hydraulic infrastructure, and building ports along rocky coastlines demands detailed understanding of marine conditions. Yet ancient builders not only overcame these obstacles but transformed them into advantages, as their settlements occupied positions that maximized trade opportunities while maintaining access to natural defensive features. The question is not whether they succeeded, because the ruins proved that they did, but rather how they accumulated enough practical knowledge to consistently make such effective engineering decisions without modern surveying instruments, geological studies, or hydrodynamic models. Among all the engineering enigmas of Beydaglari Coastal National Park, none is more fascinating than the harbour system of Phaselis, which, unlike most ancient ports, possessed 3 separate harbours positioned around a narrow peninsula extending into the Mediterranean Sea. Even today, marine engineers regard harbour construction as one of the most complex forms of infrastructure, as successful ports must account for wave energy, prevailing winds, seasonal storms, sediment transport, water depth, coastal erosion, and long-term environmental change. Modern projects rely on satellite measurements, sonar mapping, computer simulations, meteorological records, and extensive geological surveys. Yet the builders of Phaselis had none of these technologies. Despite this, archaeological surveys indicate that the city's harbours functioned effectively for centuries, serving merchant vessels moving between the Aegean, Anatolia, Cyprus, Egypt, and the Levant. The engineering challenge becomes clearer when comparing Phasaelis with other famous ancient ports, as the Roman harbour of Ostia near Rome required constant maintenance because of sediment accumulation from the Tiber River. The harbour of Alexandria underwent repeated modifications as coastal conditions changed, and even many modern marinas struggle with silting problems that reduce navigability over time. Phasaelis, however, appears to have been positioned with remarkable awareness of local marine dynamics, and researchers still debate how ancient engineers identified the most stable locations, whether through generations of sailors accumulating detailed observational knowledge of seasonal currents, builders conducting long-term monitoring of wave behavior before construction, or the existence of a sophisticated body of maritime engineering knowledge that has since disappeared. No surviving texts provide definitive answers, and the deeper researchers investigate the harbour system, the more impressive it becomes, as the harbours were not simply natural coves but were integrated into a broader urban network involving roads, warehouses, defensive structures, and commercial facilities, suggesting planning on a scale requiring significant expertise in logistics and transportation engineering, while the knowledge behind that planning remains largely invisible. Closely connected to the harbour mystery is the question of surveying, as modern surveyors can establish accurate coordinates using GPS systems capable of centimetre-level precision, whereas ancient Lycian builders relied on simple instruments, visual alignments, and practical experience. Yet many structures throughout the region display remarkable spatial organisation, with roads connecting strategically important locations, harbour entrances aligning with navigational requirements, and urban layouts demonstrating awareness of topography and drainage patterns. This raises an intriguing possibility that ancient surveyors possessed practical methods whose effectiveness modern observers tend to underestimate, since archaeologists know that Greek and Roman engineers used measuring rods, plumb lines, gromers, and sighting instruments. But what remains unclear is how these relatively simple tools consistently produced results that functioned effectively within highly complex environments. The gap between available tools and achieved outcomes continues to fuel debate among historians of technology. The Mediterranean climate presents another engineering challenge, as rainfall is highly seasonal. Summers are long and dry, and extended drought periods can place severe pressure on urban populations. Yet the ancient settlements within Beda Glari maintained reliable water supplies over long periods. Excavations have revealed reservoirs, cisterns, aqueduct components, drainage channels, and storage facilities, and together these systems indicate advanced understanding of hydraulic management. The mystery lies in the calculations, since modern engineers use mathematical models to estimate consumption rates, storage capacity requirements, evaporation losses, and seasonal variability, while ancient engineers lacked such computational tools. Nevertheless, they repeatedly constructed systems capable of supporting substantial populations, and although researchers can reconstruct the physical infrastructure and estimate volumes and capacities, they cannot fully reconstruct the decision-making process behind the designs. Questions remain about how builders determined the optimal size of reservoirs, how accurately they could predict annual water demand, and how they accounted for population fluctuations, drought cycles, or changing environmental conditions, with the answers remaining uncertain. Southern Turkey lies within an active tectonic region, and over the last 2,000 years numerous earthquakes have affected the eastern Mediterranean, causing many ancient cities to be damaged or destroyed, yet portions of Lycian and Roman structures within Beda Glari remain standing. This persistence presents another engineering puzzle, as traditional explanations often emphasize luck or favorable geology. But some researchers argue that ancient builders may have understood practical principles of seismic resistance. Massive stone blocks were frequently arranged in ways that distributed loads effectively. Foundations often rested directly upon stable bedrock, and structural designs incorporated flexibility through layered construction techniques. Comparable questions arise at sites such as Machu Picchu in Peru, where earthquake-resistant stonework continues to astonish engineers, and at Hattusa in Anatolia, where massive fortifications survived centuries of environmental stress. The evidence suggests that ancient builders possessed a far more sophisticated understanding of structural behavior than is sometimes assumed, although whether this knowledge resulted from formal engineering traditions or generations of accumulated experience remains unknown. The Lycian rock-cut tombs scattered throughout the region introduce another unresolved technological question, as many were carved directly into steep cliff faces, and even today, creating such monuments would require extensive planning, specialized access systems, and significant safety precautions. Ancient craftsmen somehow managed to cut symmetrical facades, maintain geometric proportions, and execute detailed decorative work in locations that appear extraordinarily difficult to reach, making the challenge not simply artistic but also logistical and engineering related. Workers needed stable platforms, methods for transporting tools and materials, and surveying techniques capable of maintaining accuracy while working on vertical surfaces. And although archaeologists can study the finished monuments, they still struggle to reconstruct the precise construction processes. What do you think was the true secret behind the lost engineering knowledge of the Lycian builders? Centuries of accumulated experience, a forgotten scientific tradition, or technologies that history has simply failed to preserve? Share your thoughts in the comments below. In the rocky hills of central Tanzania, hundreds of ancient paintings still cling to stone surfaces after thousands of years. Wind, rain, heat, and time should have erased them long ago, yet the images remain. The greatest mystery of Kondoa is not what was painted, but how the paint survived. The Kondoa rock art sites are located in central Tanzania, covering hundreds of shelters and rock overhangs across an area of thousands of square kilometers. Although local communities had known about the paintings for generations, systematic archaeological documentation expanded during the 20th century, eventually revealing one of the largest concentrations of prehistoric rock art in Africa. Modern paint exposed to the elements often begins deteriorating within decades. An ancient paint exposed directly to sunlight, seasonal rainfall, biological growth, and temperature fluctuations should disappear even faster. Yet many paintings at Kondoa remain visible after periods that may exceed several thousand years, creating one of the most fascinating technological mysteries in African archaeology. Scientists have identified some of the pigments used by ancient artists, with red colours commonly produced from hematite-rich ochre, white pigments likely coming from kaolin clay and other mineral sources, and black pigments often derived from carbon-based materials or manganese compounds. However, knowing the pigment does not solve the mystery, because pigment alone does not explain survival. A pile of crushed hematite placed on exposed stone would quickly wash away, meaning something else had to hold these particles together and bond them to the rock surface. Researchers suspect that ancient artists mixed pigments with binders such as plant gums, tree resins, animal fat, blood, egg-like substances, or combinations of organic materials. But the problem is that organic compounds degrade over time, leaving little evidence behind. Thousands of years later, archaeologists can often identify the mineral component, but struggle to reconstruct the complete chemical recipe. This challenge is not unique to Kondoa, as similar questions surround the paintings of Lascaux in France, Altamira in Spain, and Australia's Aboriginal rock art traditions. Yet, Kondoa presents an especially intriguing case because many paintings survived in an environment far more exposed than deep cave systems. The result is a scientific paradox. Modern laboratories can identify microscopic mineral particles and measure chemical compositions with extraordinary precision, yet the exact formula that allowed some paintings to survive for millennia remains uncertain. The artist may have possessed practical knowledge of chemistry that was never written down and has now vanished completely. The survival of the paintings raises another question about how much the artists understood about the materials they were using. Modern materials scientists know that pigment durability depends on numerous factors such as particle size, mineral composition, surface roughness, moisture exposure, chemical stability, and temperature fluctuations. Remarkably, many Kondoa paintings appear on surfaces that naturally promote preservation, with some rock faces showing relatively limited water runoff, others protected beneath natural overhangs, and certain surfaces possessing textures that help pigments penetrate microscopic pores in the rock. Today, geologists can analyze these properties using advanced instruments, but ancient artists had no such technology. Yet they repeatedly selected locations that turned out to be among the most stable surfaces available. This raises the question of whether it was simple coincidence, or whether generations of observation allowed ancient communities to recognize which rock surfaces would preserve images for the longest periods. If so, the painters may have developed a practical form of geological knowledge through centuries of experimentation. One of the least discussed mysteries of Kondoa involves the placement of the paintings themselves. The region contains countless rock surfaces suitable for drawing, yet ancient artists repeatedly chose specific shelters and overhangs. Many of these locations share common characteristics such as protection from direct rainfall, stable geological formations, broad visibility across surrounding landscapes, and natural acoustic effects. This pattern suggests deliberate selection rather than random decoration. Researchers have noted similar behaviors at prehistoric sites around the world, where, in Europe, Paleolithic artists frequently painted deep cave chambers, and in Australia, Aboriginal artists often selected locations with cultural and environmental significance. At Kondoa, the repeated preference for certain geological settings suggests a sophisticated understanding of place, though the question remains whether this understanding emerged through spiritual traditions, practical observation, or some combination of both. Although many Kondoa paintings depict people, animals, hunting scenes, and ritual activities, others feature geometric designs whose meanings remain uncertain. Researchers have documented parallel line networks, circular patterns, grid-like structures, symmetrical motifs, and repeating abstract symbols, with some designs displaying surprising consistency and proportional balance. Creating symmetrical geometric forms without rulers, measuring devices, or drafting tools is far more difficult than it appears, as even slight errors become visible when repeated patterns cover large surfaces. This raises an intriguing possibility about whether these were merely decorative motifs, or visual representations of information, ritual knowledge, territorial markers, cosmological concepts, or symbolic systems now lost to history. The answer remains unknown. Another unusual pattern has attracted increasing scientific attention, as several rock art sites worldwide appear associated with distinctive acoustic environments, where certain chambers produce echoes, amplifications, or resonance effects that differ significantly from surrounding areas. Investigations at numerous prehistoric locations have revealed correlations between sound behavior and artistic activity, and some Kondoa shelters also exhibit notable acoustic properties. Standing within these spaces, voices can reverberate unexpectedly. Certain sounds carry farther than anticipated, and echoes reflect from surrounding stone surfaces in unusual ways. Researchers continue debating whether this relationship is meaningful, questioning whether ancient communities intentionally chose locations because of their sound characteristics, or whether the connection is merely accidental. If intentional, it would suggest a sophisticated understanding of environmental acoustics long before formal science emerged. One of the most remarkable aspects of Kondoa is the evidence for repeated use over enormous spans of time, as many shelters contain multiple layers of paintings. New images were often placed over older ones, and in some cases archaeologists have identified several artistic phases separated by centuries or even millennia. This creates another mystery regarding how knowledge of these locations survived for so long. Maintaining cultural continuity across hundreds of years is difficult, and preserving traditions across thousands of years is extraordinary. The repeated return to the same site suggests that knowledge was transmitted through generations with remarkable accuracy, possibly through stories, rituals, oral traditions, and cultural memory functioning as a sophisticated information storage system capable of preserving important locations long before written records existed. Exactly how this transmission occurred remains uncertain. Deep within the Oresti Mountains of modern-day Romania, a fortress built more than 2,000 years ago continues to challenge archaeologists, engineers, and military historians. Perched high above steep valleys and protected by dense forests, Costesti Setatouie was once one of the strongest strongholds of the Dacian kingdom. Yet the greatest mystery is not why it was built, but how its builders achieved such remarkable engineering with technology that should have been far more limited than what the ruins suggest. Although known locally for centuries, systematic archaeological investigations began during the 19th and 20th centuries as researchers explored the network of Dacian fortresses surrounding Sarmizegetusa Regia, the ancient capital of Dacia, and excavations gradually revealed walls, towers, terraces, defensive systems, roads, workshops, and evidence of sophisticated construction techniques hidden beneath centuries of vegetation and soil, showing that what emerged was not a primitive hill fort but a carefully engineered military complex. The first mystery begins with location, as Costesti Setatouie occupies a steep mountain ridge, roughly 600 meters above sea level, where even today transporting construction materials into the area is difficult. Yet the Dacians managed to construct massive defensive walls, towers, platforms, and supporting infrastructure using thousands of tons of stone and timber. The challenge becomes apparent when comparing the site to other famous ancient mountain complexes, such as Machu Picchu in Peru, where Inca builders transported stone across mountainous terrain with no wheeled transport, or Sacsayhuaman, where enormous blocks weighing dozens of tons were moved uphill, making Costesti Setatouie a similar logistical puzzle under very different environmental conditions. Archaeologists estimate that many stones used in the fortress originated from quarries located kilometers away, meaning every block had to be extracted, shaped, transported, positioned, and integrated into defensive structures without modern machinery. And while no written Dacian engineering manuals survive and no detailed construction records exist, the physical evidence remains even though the knowledge system behind it has largely disappeared, raising the simple question of how a society often portrayed by Roman sources as tribal could coordinate construction projects of such complexity across rugged mountain landscapes. The most fascinating mystery of Costesti Setatouie is a construction technique known today as muros de secus, which at first glance appears relatively ordinary, but upon closer examination reveals something far more sophisticated, consisting of two parallel faces of carefully cut stone blocks with the interior filled with earth, gravel, and smaller rocks, while massive wooden beams tie the entire structure together by penetrating the stone faces and connecting the wall into a unified system. To modern engineers, this arrangement looks surprisingly familiar because rather than relying solely on the compressive strength of stone, the design distributes stress through multiple materials working together, with stone handling compression, wood absorbing tension and dynamic movement, and the internal fill dissipating energy and stabilizing the structure, resembling in modern terminology a composite engineering system. The mystery lies in the fact that such principles are generally associated with much later structural design philosophies, and researchers studying reconstructed sections have noted that Murus behaves differently from conventional dry stone walls, appearing capable of absorbing shock, accommodating minor ground movement, and resisting collapse more effectively than many simpler fortification designs, with some engineers even suggesting that the combination of stone and timber may have offered advantages during seismic activity, although the exact degree of earthquake resistance remains debated. What deepens the mystery is the absence of a clear developmental pathway, as Greek fortifications use different approaches, Roman military walls followed different principles, and Celtic fortifications sometimes incorporated timber-laced structures. But Murus possesses distinctive characteristics not easily explained as a direct copy of neighbouring traditions, leading to questions about whether the Dacians independently discovered these structural concepts, whether knowledge travelled through networks now lost to history, or whether archaeologists are seeing only the final product of centuries of experimentation that left little trace in the archaeological record, with no consensus existing even more than 2,000 years after construction, as the walls continue to raise questions that modern engineering cannot answer with certainty. The fortress reveals another surprising feature in its precision, as laser surveys and archaeological mapping have shown that the defensive structures were not placed randomly according to the terrain, but instead followed carefully planned layouts where terraces align with defensive objectives, walls maximize natural advantages, observation points maintain strategic visibility over approaches, and movement corridors channel attackers into predictable routes, all of which required accurate surveying. This is where the mystery becomes significant because the Dacians possessed no total stations, laser levels, GPS receivers, drones, or digital mapping systems. Yet they successfully transformed an irregular mountain landscape into an integrated defensive machine, similar to how ancient builders elsewhere achieved comparable feats, such as Roman engineers surveying roads across continents, Egyptian architects aligning pyramids with extraordinary precision, and the Inca designing cities perfectly adapted to mountainous terrain. Placing Costesti's Setatui within this category of engineering achievements, where the ruins demonstrate the result while the process remains largely invisible. Costesti's Setatui was never intended to operate alone, but formed part of a larger defensive network that included multiple fortresses protecting the Dacian heartland. And while each fortress appears impressive when viewed individually, collectively they reveal something much more remarkable as communication routes linked strategic positions, observation points, monitored valleys and mountain passes, fortified sites controlled movement through the region, and resources and manpower could be coordinated across significant distances. Military historians often compare the system to a distributed defensive network rather than a collection of isolated strongholds, raising the important question of how advanced Dacian organizational capability was, since building a single fortress requires planning, but constructing an interconnected mountain defense system requires administration, logistics, engineering, communication, and long-term strategic thinking, which helps explain the fierce Dacian resistance described in Roman sources during Emperor Trajan's campaigns in the early 2nd century AD, as the fortresses were not simply walls, but components of a regional military architecture. Every mountain fortress faces the same challenge of water, as a garrison cannot survive without reliable access to fresh water, especially during a siege. And at Costesti Ketatui, archaeologists have uncovered evidence suggesting sophisticated management of water resources through terraces, drainage systems, and strategic placement of structures that indicate builders carefully considered hydrology. Although this may sound routine, it was not, because mountain environments are notoriously difficult for long-term settlement, where too little water creates vulnerability and too much water destabilizes slopes, damages foundations, and accelerates erosion. Yet the fortress survived for centuries because its builders successfully balanced these competing forces, achieving results comparable to modern geotechnical engineers who routinely analyze drainage before constructing on steep terrain, even though the Dacians did so without modern hydrological science, leaving unclear how they accumulated this knowledge. Costesti Ketatui has withstood over 2,000 years of harsh conditions, freezing winters, heavy rains, erosion, and seismic activity, yet much of the fortress remains intact. Foundations still stand, defensive layouts are visible, and terraces shape the landscape. This durability suggests the builders had a strong understanding of stable terrain and long-lasting construction methods, even though their knowledge has been lost. In the valleys of Jalisco, western Mexico, stands an archaeological site unlike almost anything else on Earth. While ancient civilizations from Egypt to Mesopotamia and Mesoamerica built square temples and rectangular cities, the builders of Los Guachimontones created something radically different. Giant circular pyramids arranged in perfect concentric rings. More than 1,000 years after the civilization vanished, archaeologists still cannot fully explain why. Located near Tuchitlan in the state of Jalisco, Los Guachimontones remained largely unknown to the outside world until systematic archaeological investigations accelerated during the late 20th century. Excavations revealed the ceremonial center of a sophisticated culture that flourished roughly between 300 BCE and 900 CE, now known as the Tuchitlan tradition. What emerged from the soil surprised researchers, as instead of the familiar pyramids of Mesoamerica, they found an entire architectural system based on circles. The most important question surrounding Los Guachimontones is also the simplest. Why did its builders choose circles? Throughout history, monumental architecture overwhelmingly favors straight lines and right angles. The Great Pyramid of Giza uses a square base. The temples of the Maya employ rectangular platforms. Roman cities were organized through grids, and even the vast ceremonial centers of Teotihuacan followed geometric axes based on straight avenues. Circular monumental architecture exists elsewhere, but usually on a much smaller scale, making Los Guachimontones distinctly different. The largest circular complexes exceed 100 meters in diameter, with each featuring a stepped conical pyramid at the center, surrounded by concentric platforms and courtyards, all radiating outward from a central point with remarkable symmetry. From an engineering perspective, this choice created challenges that would have been unnecessary with rectangular construction. A square can be laid out using ropes stretched between four corners, whereas a circle requires accurate determination of a central point and consistent measurement of radius around the entire circumference, where small errors become increasingly visible as the structure grows larger. Modern surveyors achieve this using precision instruments, yet the builders of Los Guachimontones had neither steel measuring devices nor optical surveying equipment. Despite this, aerial surveys reveal astonishing geometric consistency. Some researchers suggest that ropes anchored to a central stake could have been used to establish circles, but while plausible, this explanation merely shifts the mystery. Maintaining accuracy across multiple construction phases over decades or even centuries would have required a sophisticated understanding of measurement and planning that remains poorly understood. The question is not whether they could build circles, as the evidence proves they could, but rather why they invested enormous resources into a design far more difficult than conventional alternatives. Some archaeologists believe the circles represented cosmological concepts. Others argue they functioned as ceremonial theatres designed to focus communal gatherings toward a sacred centre, and still others see astronomical symbolism embedded within the layout. However, no theory fully explains every feature, and more than 1,000 years later, the true motivation remains unknown. Standing above Los Guachimontones today, the site appears almost modern in its geometric clarity, with the concentric arrangement creating a level of order rarely seen in pre-Columbian architecture. Archaeologists have measured recurring proportions throughout the site, where certain distances appear repeatedly, suggesting standardized planning methods and indicating that the builders clearly understood how to reproduce complex layouts across multiple ceremonial centers. This presents another puzzle, as the Tuxtlan culture left no known written mathematical treatises, no construction manuals survive, and no diagrams explain how measurements were transferred from concept to reality. Yet the architecture demonstrates practical mastery of geometry. This problem appears repeatedly throughout archaeology, as seen at Stonehenge, where researchers still debate how Neolithic builders achieved long-distance alignments, at Machu Picchu, where questions remain regarding surveying methods used in mountainous terrain, and at Sacsayhuaman, where the precision of stone placement continues to fascinate engineers. Los Guachimontones belongs within this same category of mystery, where the structures reveal what ancient builders achieved, but not how they learned to achieve it. At the center of several circular complexes, archaeologists discovered evidence of massive wooden poles that may have reached heights exceeding 15 meters and possibly much more. Many researchers connect them to the Volador ritual, a ceremony in which participants descended from elevated poles while suspended by ropes. If this interpretation is correct, another engineering question emerges. How were such enormous poles transported, erected, and stabilized? Raising a vertical timber of that size requires careful control of weight, leverage, and balance, and even in modern construction, erecting tall poles demands planning and coordination. The Tuxtlan builders accomplished this without cranes, steel cables, or mechanized lifting systems. No definitive reconstruction exists, although experimental archaeology has demonstrated possible methods involving ramps, ropes, and large labor forces. However, direct evidence remains limited, and the exact procedures used by the original builders remain uncertain. One of the most underestimated mysteries of Los Guachimontones is not architectural but logistical. As building monumental structures requires more than engineering, it requires social organization. The larger circular complexes contain vast volumes of earth and stone, with thousands of tons of material needing to be quarried, transported, shaped, and assembled. Researchers estimate that major construction projects would have required coordinated labor involving large segments of the surrounding population. This raises important questions about how workers were organized, who directed construction, and how specialized knowledge was transmitted between generations. Unlike the Egyptians, whose achievements were recorded in inscriptions, the Tuxtlan culture left relatively few written clues. The buildings survive, but the organizational system behind them largely does not. The circular form has led some researchers to investigate potential astronomical connections, as many ancient civilizations incorporated celestial observations into architecture. The Maya tracked Venus with extraordinary precision. Egyptian pyramids exhibit alignments connected to cardinal directions, and the builders of Stonehenge incorporated solar cycles into monument placement. This raises the question of whether Los Guachimontones represents a similar tradition. Several studies have explored possible alignments involving solar events and seasonal cycles, with some researchers arguing that the concentric layout may have helped structure ceremonial activities linked to agricultural calendars. However, the challenge lies in separating intentional design from coincidence, as given enough structures, some alignments naturally occur by chance. At present, the evidence remains intriguing but inconclusive, and the astronomical hypothesis continues to generate debate rather than consensus. Excavations have revealed evidence that the people of Los Guachimontones participated in extensive exchange networks, with materials and artifacts found at the site indicating connections extending across western Mexico and beyond. This discovery surprised many researchers, as the traditional image of isolated regional communities does not fit the archaeological evidence. Maintaining long-distance trade requires knowledge of routes, resources, negotiation, and logistics, as well as stability. The existence of these networks suggests that the society responsible for Los Guachimontones was more economically sophisticated than once believed. Yet many details remain unclear, and researchers continue to debate the scale, structure, and administration of these exchange systems. What do you think was the true reason behind the construction of the world's most mysterious circular pyramids? Share your theory in the comments below. High in the northern Andes of Peru, more than 2,300 meters above sea level, lies Huasi, a ceremonial center older than the Inca, older than Machu Picchu, and home to engineering mysteries that modern archaeology still struggles to explain. Although local communities had long known of the site, systematic archaeological investigations during the 20th century revealed a monumental ceremonial complex dating roughly between 1250 BCE and 50 BCE, where excavations uncovered temples, underground galleries, sophisticated stone architecture, and some of the most remarkable ancient gold artifacts ever found in the Andes. At first glance, Huasi seems modest compared with famous sites such as Machu Picchu, Teotihuacan, or Petra. Yet archaeologists quickly realized that its importance lies not in its size, but in its technological sophistication. The site emerged during a period when much of the Andean world was still developing large-scale ceremonial architecture, yet the builders of Huasi were already manipulating stone, controlling water, creating underground structures, and producing luxury metal objects with a degree of skill that appears surprisingly advanced for the era. Radiocarbon dating places major phases of construction between approximately 800 and 200 BCE, meaning many of the site's achievements predate the Roman Empire, the Great Wall of China, and numerous classical civilizations often associated with monumental engineering. The deeper researchers investigate Huasi, the more a difficult question emerges: where did this knowledge come from? One of the most striking features of Huasi is its stone architecture, where many blocks display carefully flattened surfaces and deliberate shaping. While they do not reach the extreme polygonal precision later seen at Sacsayhuaman, they demonstrate a level of planning that required far more than simple trial and error. The challenge becomes apparent when considering the available technology, as there is no evidence that the builders possessed iron tools, steel was completely unknown, and most tools were likely made from stone hammers, harder rocks, and early copper-based implements. Modern experiments show that shaping volcanic or sedimentary stone using such tools is possible, but achieving consistency across large construction projects demands extensive knowledge of materials and technique. Researchers can explain how an individual block might have been carved, yet what remains less clear is how entire generations developed standardized construction methods capable of producing complex ceremonial architecture over centuries. The problem resembles questions raised at Stonehenge, Göbekli Tepe, and early Egyptian monuments, where the structures themselves survive but the educational system that trained the builders does not. Beneath portions of the ceremonial complex are underground galleries and chambers, and although constructing underground spaces may sound simple today, it presents serious engineering challenges because every roof must withstand enormous pressure from the earth above, and even minor miscalculations can lead to collapse. Yet, many of Kuntur-Wasi's subterranean structures remained stable for centuries. Modern engineers calculate such loads using mathematical models, geological surveys, and structural analysis software. But ancient builders possessed none of these tools. Nevertheless, they somehow determined wall thicknesses, support geometry, and stone placement accurately enough to preserve these spaces for more than 2 millennia. This raises an uncomfortable question for archaeology. Were these achievements the result of accumulated practical experience spanning hundreds of years? Or did the builders possess a systematic understanding of structural behavior that has been lost? The answer remains uncertain. The Andes experienced dramatic seasonal rainfall variations, and without proper drainage, ceremonial centers built from earth and stone would rapidly deteriorate because water infiltration can weaken foundations, destabilize slopes, and destroy architectural features. Excavations at Kuntur-Wasi have revealed evidence of drainage channels and carefully prepared construction surfaces designed to control runoff, which from an engineering perspective is extremely significant. Effective drainage requires understanding gradients, water flow patterns, and long-term erosion processes, and modern civil engineers still devote substantial effort to solving these problems. The builders of Kuntur-Wasi appear to have solved them through observation and experience. Yet, what remains unknown is the exact method they used to predict water behavior across the site. No written manuals survive, no mathematical records exist, yet the results suggest knowledge that was both practical and highly effective. Among the most recognizable discoveries at Kuntur-Wasi are large stone sculptures and carved monoliths, several of which feature complex iconography associated with elite ritual traditions, and their craftsmanship indicates highly specialized artisans capable of maintaining symmetry and detail across large surfaces. The engineering challenge begins long before carving, as many stones had to be extracted, transported, positioned, and erected in mountainous terrain. Even today, moving multi-ton blocks across steep landscapes requires planning, labor coordination, and mechanical advantage. Researchers estimate that transporting such stones would have demanded organized workforces and carefully designed logistics systems. Comparable mysteries appear at Tiwanaku in Bolivia, the Moai platforms of Easter Island, and certain megalithic structures in Europe. The question is not whether ancient people could move large stones, as the evidence proves they could, but the mystery lies in how they repeatedly accomplished these feats with such consistency. Perhaps the most fascinating technological mystery at Kuntur-Wasi comes not from its stone architecture but from its gold, as excavations uncovered an astonishing collection of ceremonial gold artifacts, including crowns, ornaments, pectorals, earrings, and ritual objects associated with elite burials, some of which date to nearly 2,500 years ago. What makes them remarkable is not merely their age but their sophistication. as metallurgical analyses show evidence of advanced metalworking techniques, including hammering, annealing, shaping, polishing, and the controlled manipulation of precious metals. Annealing is particularly important, as this process involves heating metal to specific temperatures and then cooling it to restore workability. And without proper temperature control, gold can become difficult to shape or suffer structural weaknesses. Modern metalworkers monitor such processes using thermometers and precise equipment, yet ancient craftsmen possessed neither, and still microscopic examinations indicate that Kuntur-Wasi artisans repeatedly achieved successful results. Even more surprising is the thinness of certain gold sheets, as some decorative elements required transforming relatively small amounts of metal into broad, visually impressive surfaces while avoiding tears or fractures, which demands an intimate understanding of material behavior. Comparisons with contemporary cultures reveal that Kuntur-Wasi belonged to a select group of early societies developing sophisticated metallurgy, with similar advances appearing in parts of the Near East, Egypt, and later Mediterranean civilizations. However, unlike those regions, the Andes developed metallurgy independently, meaning Kuntur-Wasi's craftsmen were not simply copying foreign technology, but were creating their own. The greatest mystery is how such specialized knowledge was transmitted, as no technical manuals survive and no instructional texts exist. Archaeologists can analyze the finished objects, but reconstructing the complete manufacturing sequence remains extraordinarily difficult. And in many ways, the gold artifacts represent a lost science, demonstrating mastery while concealing the learning process that made that mastery possible. Researchers have long debated whether the layout of Kuntur-Wasi incorporated astronomical alignments, as several architectural elements appear oriented towards significant solar positions along the horizon, and if intentional, such alignments would require decades of observation. Ancient observers would need to track seasonal movements of the sun, identify recurring patterns, and integrate those patterns into construction plans. Similar debates surround Stonehenge, Chichen Itza, Machu Picchu, and Newgrange, where the challenge is distinguishing deliberate design from coincidence. At Kuntur-Wasi, evidence suggests at least some relationship between architecture and celestial observation, but the full extent remains uncertain. Overlooking the Guadalbolon Valley near Jaén in southern Spain stands an ancient Iberian city that may preserve one of the most precise solar alignments ever discovered in pre-Roman Europe. At Puente Tablas, a gate built more than 2,500 years ago, appears to have been designed to capture the sunrise of the winter solstice with astonishing accuracy, and the structure still works today, raising the question of how its builders achieved it. Although the hill had long been known locally, systematic archaeological excavations began during the late 20th century, revealing not a simple settlement but a fortified Iberian oppidum, covering roughly 6 hectares and occupied primarily between the 7th and 4th centuries BCE. Excavations uncovered houses, defensive walls, ritual spaces, towers, and eventually a discovery that transformed the site into one of the most important archaeological mysteries in Spain, as the eastern gate of the city appeared to be aligned with a specific astronomical event. At first, this seemed unlikely because ancient gates are often oriented according to terrain, defense, or convenience, yet repeated observations suggested something far more deliberate. Every year around the winter solstice, the shortest day of the year, the rising sun appears on the southeastern horizon at its most southerly point, and at Puente Tablas, archaeologists observe that sunlight entering through the eastern gate follows a carefully controlled path and illuminates a sacred area beyond the entrance, a phenomenon that occurs only during a narrow seasonal window and carries extraordinary implications. To understand why, consider the challenge facing ancient engineers, as the position of sunrise changes every day throughout the year, and at the latitude of Jaen, approximately 38 degrees north, the sunrise point shifts across a large section of the horizon between summer and winter, meaning that identifying the precise position of the winter solstice requires years of observation. Unlike modern astronomers, the Iberians possessed no telescopes, precision optics, GPS systems, digital clocks, or computerized models, yet the gate alignment appears intentional. Researchers studying the site have suggested that the builders may have tracked solar movements for generations before construction began, requiring a sophisticated tradition of astronomical knowledge passed from one generation to another. The mystery becomes deeper when compared with other ancient solar monuments, such as the famous Passage Tomb of Newgrange in Ireland, which captures sunrise during the winter solstice, Stonehenge, which aligns with important solar events, and the temples of ancient Egypt, which often incorporated astronomical orientations. Yet Puente Tablas belongs to a civilization that left far fewer written records, and although the monument demonstrates a level of astronomical precision comparable to some of the most famous ceremonial sites in the ancient world, the knowledge system behind it remains largely invisible. Questions remain unanswered, including how Iberian builders determined the correct angle, how many years of observations were required, whether they used fixed markers on surrounding hills, and whether specialized astronomer priests were responsible for the measurements, as no definitive answers have emerged. At first glance, the Eastern Gate appears defensive, but closer examination reveals a more complex design in which the entrance forces movement through controlled pathways, preventing approaching visitors from walking straight into the city and instead manipulating visibility, movement, and perspective. This combination of military and ceremonial functions presents another puzzle, as modern architects often separate sacred and defensive spaces, yet at Puente Tablas they seem deliberately integrated. The builders created an entrance capable of controlling armies while simultaneously functioning as a giant astronomical instrument, demonstrating remarkably sophisticated dual-purpose engineering. And even more surprising is that no surviving Iberian text explains how the design process worked, leaving the structure intact but the methodology unknown. Building an astronomical alignment requires much more than observing the sun, as it also requires surveying, and while today surveyors rely on laser instruments, satellite positioning systems, total stations, and digital elevation models capable of measuring terrain with centimeter-level precision, the engineers of Puente Tablas possessed none of these technologies. Nevertheless, the city occupies a strategically selected hilltop overlooking the surrounding valley, with defensive walls following terrain contours efficiently, access routes carefully controlled, and visibility across the landscape maximized. This raises an important question about how ancient surveyors measured angles, elevations, distances, and sight lines accurately enough to combine military requirements with astronomical precision. Experimental archaeologists have attempted to reproduce ancient surveying methods using ropes, wooden stakes, plumb lines, and observation poles, and while such techniques can achieve impressive results, reproducing the exact accuracy seen at Puente Tablas remains challenging, suggesting that the final structure reflects knowledge far beyond simple trial and error. Excavations reveal that the city was protected by substantial fortifications, with walls, towers, gates, and restricted access points working together as a coordinated defensive system. Military historians often compare effective ancient fortifications to mechanical devices in which every component serves a specific function, and removing one element weakens the entire defensive strategy. And Puente Tablas appears to follow this principle as the gate channels movement, the walls exploit natural terrain, and the towers extend observation range, allowing the entire system to operate as an integrated design. What remains unclear is how such knowledge developed, as many ancient societies improved defences gradually over centuries through warfare and adaptation. Yet parts of Puente Tablas appear surprisingly mature from an engineering perspective, giving the impression that builders already understood sophisticated defensive concepts before construction began, leaving the origin of that expertise unanswered by archaeology. One of the most overlooked mysteries at Puente Tablas concerns urban organisation, as excavations indicate that residential zones, public areas, defensive structures and ritual spaces were not randomly distributed, but instead formed an organised urban landscape. This challenges older assumptions about Iberian settlements, since for decades many scholars viewed pre-Roman Iberian communities as relatively simple compared with later Roman cities, yet Puente Tablas suggests otherwise by demonstrating evidence of planning, coordination and long-term development. Roads connect key areas efficiently, important buildings occupy strategic locations, and public and sacred spaces appear intentionally separated. Principles that modern urban planners would immediately recognize, yet no surviving documents explain how ancient planners made these decisions, leaving the city itself as the only surviving blueprint. What do you think was the true secret behind Puente Tablas' Solar Gate? Generations of astronomical observation, a lost surveying technique, or a forgotten scientific tradition? Share your theory in the comments below. North of Xi'an, China, lies an underground empire more than 2,000 years old. Hidden beneath layers of earth, Han Yangling appears at first to be another imperial tomb. Yet the deeper archaeologists dig, the more they uncover evidence of engineering knowledge that remains only partially understood. From mass-produced terracotta figures to mysterious underground environmental control systems, Han Yangling raises an unsettling question. How did ancient builders achieve such technical sophistication without leaving behind the knowledge that made it possible? Construction work near Xi'an in the 1970s revealed unexpected underground structures, and subsequent excavations identified the site as the mausoleum complex of Emperor Jing of Han, who ruled China between 157 and 141 BCE. What initially appeared to be a royal tomb soon proved to be one of the largest and most technologically intriguing archaeological sites of the Western Han dynasty. Modern surveys reveal that Han Yangling was never intended to be merely a burial chamber, but rather an entire underground landscape. The mausoleum complex covers dozens of square kilometers and includes the emperor's tomb, the empress's tomb, ceremonial areas, storage pits, workshops, roads, and hundreds of subsidiary burial features, all demonstrating a remarkable level of spatial organization. Many structures align with consistent directional orientations across large distances, suggesting advanced surveying methods. Today, engineers achieve such precision using satellite positioning, laser measurements, and digital mapping, yet Han Dynasty planners possessed none of these technologies. Still, the geometric consistency of the site suggests a sophisticated understanding of measurement, alignment, and large-scale project planning. The challenge becomes even more remarkable when considering the terrain, as maintaining accurate positioning across a vast construction zone requires controlling cumulative measurement errors, where even small mistakes can become significant when multiplied across kilometers of construction. Somehow, the builders achieved a level of coordination that allowed separate teams to create an integrated underground complex functioning as a unified design, raising a mystery that remains difficult to answer because archaeologists can measure the final result, but the methods used to create it remain largely invisible. Among the most extraordinary discoveries at Hanyangling are tens of thousands of miniature terracotta figures, which, unlike the famous life-sized warriors of Qin Shi Huang, are significantly smaller, typically measuring between 50 and 60 centimeters in height, with many originally wearing real silk clothing and carrying wooden arms that have long since decayed. At first glance, the figures appear simple, but closer examination reveals something astonishing, as researchers have identified evidence suggesting standardized production methods in which heads, torsos, arms, and legs appear to have been manufactured separately and assembled later. Certain facial features and body proportions recur with striking consistency, and tool marks indicate repetitive manufacturing processes rather than entirely individual sculpting. This has led some scholars to compare the production system to a primitive assembly line, a comparison that is remarkable because large-scale standardized manufacturing is often associated with much later historical periods. Yet Hanyangling suggests that craftsmen more than 2 millennia ago may have developed efficient production techniques capable of generating enormous quantities of highly consistent artifacts. The question is not whether they succeeded, as the evidence proves they did, but rather how the production system was organized, including how quality standards were maintained, how molds were distributed, and how thousands of components were coordinated before final assembly. The physical objects survive, but the manufacturing knowledge does not. Perhaps the most intriguing engineering puzzle at Hanyangling lies beneath the artifacts themselves, as many burial pits preserved organic materials far better than expected for structures more than 2,000 years old. Fragments of textiles, wood residues, pigments, and delicate materials survived in environments that should have accelerated decay, leading scientists studying the site to point toward a combination of factors. Depth played a role, soil composition played a role, groundwater behavior played a role, and oxygen availability likely influenced preservation, with these factors together creating stable underground microenvironments capable of slowing destructive biological and chemical processes. The remarkable aspect is not that such conditions existed, but that they appear repeatedly. Modern conservation science recognizes that stable temperature, controlled humidity, and limited oxygen exposure significantly reduce deterioration, and museums spend enormous resources maintaining these conditions artificially. Yet Hanyangling seems to have achieved comparable environmental stability through architecture and geology alone. Some burial chambers remained remarkably consistent despite seasonal weather changes occurring above ground, as thick layers of earth functioned as natural thermal insulation. Certain soil compositions may have regulated moisture movement, and burial depth reduced temperature fluctuations that would otherwise accelerate material degradation. The question is whether these effects were intentional, raising further inquiries about whether Han engineers understood enough about underground environments to design preservation systems deliberately, or whether they were unknowingly benefiting from favorable geological conditions. This distinction is important because deliberate environmental control would imply a practical understanding of soil physics, groundwater dynamics, airflow behavior, and long-term material preservation far beyond what historians usually associate with ancient engineering. Modern instruments can measure humidity gradients and thermal behavior inside excavation zones, and model oxygen diffusion and moisture transport through soil layers, yet these tools still cannot determine with certainty whether the ancient builders intentionally engineered the microclimate. As a result, Hanyangling occupies a fascinating position between archaeology and environmental engineering, demonstrating that effective preservation occurred while not fully explaining how much the builders understood about the processes responsible. The burial pits themselves present another challenge, as many extend tens of meters in length and require the removal of enormous quantities of earth. The region around Xi'an is dominated by loess, a fine-grained sediment known for both its stability and its unpredictability, as it can stand in steep vertical faces under certain conditions, yet also collapse catastrophically when moisture changes weaken its structure. Modern geotechnical engineers rely on soil testing, mathematical modelling, and stability calculations before excavating large underground spaces. But Han Dynasty builders had no such tools. Nevertheless, the pits at Han Yangling were constructed successfully and remained intact for centuries, implying an accumulated body of practical knowledge regarding soil behaviour. Builders appear to have understood how deep excavations could safely proceed, how walls should be shaped, and how structural failure could be minimised. This challenge resembles mysteries seen elsewhere in the ancient world, as engineers studying the underground city of Derinkuyu in Turkey, the rock-cut architecture of Petra, and the subterranean complexes beneath Egypt encounter similar questions, where the structures exist but the practical knowledge that created them has largely disappeared. Which mystery of Han Yangling fascinates you most? Share your thoughts in the comments below. Far from the pyramids of Egypt and the stone cities of the Maya, archaeologists uncovered something that should not exist in northern Peru. Hidden beneath layers of ancient construction at Ventaral was a painted mural more than 4,000 years old, one of the oldest known murals in the Americas. Yet the mural itself may not be the greatest mystery, because the real mystery is how a civilization with no known writing system, no metal tools, and seemingly simple technology created structures, artworks, and engineering solutions that still challenge modern explanations. Ventaran remained largely unknown until archaeological investigations in the early 21st century revealed a ceremonial complex buried beneath centuries of construction, and radiocarbon dating pushed parts of the site back to roughly 2500 BCE, making it contemporary with some of the earliest monumental traditions in the ancient world. What researchers found beneath the sands would force a re-evaluation of technological development in ancient Peru. The most astonishing discovery at Ventaran was a painted wall depicting a deer-like figure trapped in a net, which at first glance appears to be a simple religious image. Yet, from an engineering perspective, the mural raises questions that remain unresolved. Painted surfaces are fragile, and even in modern buildings, pigments often fade within decades when exposed to moisture, temperature changes, salt crystallization, biological growth, and structural movement. Yet, Ventaran's mural has survived for more than 4 millennia. The survival of the image is not merely a matter of luck, as scientific analysis indicates that the builders prepared multiple layers of plaster before applying pigments derived from mineral sources, meaning the wall was not randomly painted but carefully engineered. The puzzle lies in the level of material understanding required, as ancient craftsmen somehow selected pigments compatible with their plaster base, controlled adhesion well enough to prevent large-scale separation, managed moisture migration through the wall, and created a surface stable enough to preserve colour across thousands of years of environmental change. Comparable preservation challenges appear in Egyptian tomb paintings, some of which survived over 3,000 years, yet Egypt possessed a far more extensively documented civilization, complete with specialized artisans and organized state projects, whereas Ventaran emerged from a society that left behind far fewer written clues regarding its technical knowledge. Modern conservation scientists can identify pigments and analyze mineral composition under microscopes. But what remains unclear is how ancient builders acquired this knowledge through practical experience alone, as no surviving manual explains the process and no technical instructions remain, leaving the mural intact while the knowledge system behind it has largely disappeared. Another mystery emerges from the architecture itself, as Ventaran was constructed primarily using adobe, clay, mud plaster, and locally available materials, which to modern observers may appear simple compared with stone monuments such as the Great Pyramid or Machu Picchu, although engineers know the opposite is often true because Earth is unpredictable, expanding and contracting with moisture, cracking under thermal stress, and weakening when exposed to prolonged water infiltration, meaning that designing large structures from Earth requires understanding soil behavior, load distribution, drainage, and long-term settlement. Yet many of Ventaran's structures remained recognizable after thousands of years, and researchers studying earthen architecture frequently compare such sites with later adobe centers across Peru and with massive mud brick cities of Mesopotamia, where in many cases continuous maintenance was necessary to ensure survival, suggesting that Ventaran's endurance indicates its builders possessed a practical understanding of construction techniques far beyond what is typically assumed for societies of this age. The mystery is not whether they succeeded, because the structures prove they did, but rather how they learned enough about material behavior to succeed so consistently. Walking through the ceremonial spaces of Ventaran reveals another puzzle, as the arrangement of walls, plazas, and ritual chambers does not appear random, with architectural elements following coherent spatial plans, alignments remaining surprisingly consistent, and certain areas displaying clear evidence of deliberate organization and geometric thinking. Today, surveyors rely on lasers, GPS systems, total stations, and digital mapping software. Yet ancient builders possessed none of these technologies, raising the question of how measurements were established. One possibility involves rope-based surveying systems similar to those documented in Egypt, while another theory proposes observation of celestial bodies combined with simple geometric techniques, and experimental archaeologists have demonstrated that surprisingly accurate layouts can be achieved using cords, stakes, and repeated measurements. However, demonstrating possibility is not the same as explaining reality, as no direct evidence reveals the exact methods used at Ventaran, leaving the architectural precision visible while the measuring system remains largely invisible. This challenge appears repeatedly across ancient archaeology, from Machu Picchu, where researchers continue studying how Inca builders achieved remarkable structural alignment in difficult terrain, to Stonehenge, where debates persist regarding surveying methods, placing Ventaran in the same category of mystery, evidence of competence without complete evidence of process. The scale of construction raises questions extending beyond engineering, because monumental projects require people, and workers must be fed, materials must be transported, construction schedules must be coordinated, and knowledge must be transmitted across generations. Ventaran was not an isolated hut built by a handful of individuals, but formed part of a broader ceremonial landscape in northern Peru, associated with increasingly complex social organization, and archaeologists estimate that major construction efforts in ancient societies often required hundreds or thousands of laborers over extended periods, implying administration, planning, and logistical coordination. Yet the organizational mechanisms remain largely hidden, as unlike later civilizations that left extensive records, Ventaran offers only fragments, allowing researchers to estimate labor requirements, reconstruct construction sequences, and analyze architectural phases, but not fully reconstruct the decision-making system that coordinated everything. The result is a paradox in which the physical evidence demonstrates sophisticated management, while the management system itself has almost vanished. Some researchers have also noted intriguing properties within ceremonial architecture throughout ancient Peru, where certain enclosed spaces appear capable of amplifying sound, Narrow passages channel voices, and chambers create echoes, suggesting that ritual participants may have experienced unusual acoustic effects, although whether this was intentional remains debated. If deliberate, it would suggest practical experimentation with sound long before formal acoustics existed as a scientific discipline, similar to discussions surrounding sites such as Chavan de Huantar, where engineered sound environments may have enhanced religious experiences. Modern acoustic modelling can simulate how these spaces behave, yet simulations cannot determine whether ancient builders understood the underlying principles or simply refined designs through generations of observation. And once again the same pattern emerges, where the result is visible, but the intellectual pathway leading to the result remains uncertain. In the harsh deserts of northern Mexico, hundreds of kilometers from tropical forests and major rivers, an ancient city rose from the dust, where its builders created multi-story adobe buildings, sophisticated water systems, long-distance trade networks, and perhaps the strangest industry ever discovered in ancient North America, the large-scale breeding of tropical scarlet macaws. Today, archaeologists call it Casas Grandes, or Paquime, and while the ruins reveal extraordinary achievements, the methods behind them remain one of archaeology's greatest unsolved mysteries. Although local communities had known about the ruins for centuries, systematic archaeological investigations began in the 19th century and expanded significantly during the 20th century, and excavations revealed that beneath the desert surface lay the remains of a vast urban centre, occupied primarily between approximately AD 1200 and 1450, covering more than 36 hectares and supporting a population estimated between 2,000 and 5,000 inhabitants. And what researchers uncovered challenged many assumptions about pre-Columbian societies in northern Mexico. At first glance, the architecture of Casas Grandes appears impossible, as the city was built largely from adobe, a material made from mud, clay, water, and organic fibers, which is inexpensive and effective in dry climates but has significant structural limitations since modern engineers know that large adobe structures are vulnerable to erosion, moisture damage, and collapse under excessive loads. Yet archaeological evidence suggests that some buildings at Paquime rose as high as 5 to 7 stories, and even today, constructing multi-story adobe structures requires careful control of wall thickness, load distribution, moisture protection, and foundation stability. While ancient builders had no steel reinforcement, no concrete, and no modern structural calculations, so although researchers can measure surviving walls and reconstruct probable floor plans, a fundamental question remains unanswered. How did the builders develop enough practical engineering knowledge to construct entire residential complexes that could support thousands of people? The challenge becomes even more remarkable when compared with other adobe civilizations, because at sites such as the ancient city of Chan Chan in Peru, one of the largest adobe complexes ever constructed, builders worked in a coastal environment with access to substantial labor resources and centralized administration, whereas Casas Grandes achieved similarly impressive results in a much harsher, semi-arid landscape, and the architectural sophistication suggests generations of accumulated knowledge, yet almost none of the technical instructions behind that knowledge survive. The survival of a large urban population in the Chihuahua Desert raises another mystery, as water management systems discovered throughout the site include canals, reservoirs, drainage channels, and distribution networks that appear carefully planned, and archaeologists have identified features suggesting that water was not merely collected, but actively managed and directed throughout parts of the settlement. The engineering challenge was enormous, because hydraulic systems require precise control of gradients, since if a canal descends too steeply, water accelerates and erodes its banks, while if the slope is too shallow, sediment accumulates and flow becomes unreliable. And although modern hydraulic engineers solve these problems using surveying equipment, mathematical calculations, and computer models, ancient builders relied on observational methods that remain poorly understood. Yet some canal segments maintain remarkably consistent gradients over considerable distances, leading researchers to continue debating how such accuracy was achieved without advanced instruments. And the situation invites comparisons with hydraulic systems at Petra, Machu Picchu, and Angkor, where in each case engineers transformed difficult environments into sustainable urban centres, placing Casas Grandes within that conversation despite receiving far less attention. So the mystery is not whether the system worked, because the city itself proves that it did, but rather how its designers acquired the knowledge necessary to make it work. Viewed from above, Paquime appears less like a village that expanded organically and more like a city following an intentional design, where residential compounds, ceremonial spaces, plazas, storage areas, and transportation corridors appear organized according to a coherent urban plan. And this level of planning implies the existence of administrators, surveyors, builders, and logistical coordinators capable of managing complex projects over long periods. Yet unlike civilizations such as the Maya, Egyptians, or Romans, the inhabitants of Casas Grandes left no extensive written records explaining their methods, meaning there are no engineering manuals, no construction blueprints, and no surviving archives describing urban development. So although archaeologists can see the final product, the intellectual system that produced it remains largely invisible, resulting in a paradox frequently encountered in archaeology. The physical achievements survive, while the knowledge that created them disappears. Perhaps the most astonishing mystery at Casas Grandes involves birds, not ordinary desert birds, but tropical scarlet macaws, which naturally inhabit humid tropical forests hundreds and sometimes more than 1,000 kilometers south of the Chihuahua Desert, requiring conditions dramatically different from the arid environment surrounding Paquime. Yet excavations have uncovered overwhelming evidence that macaws were not merely imported but were bred, as researchers discovered specialized aviaries, eggshell fragments, juvenile remains, nesting evidence, and large concentrations of macaw bones, strongly indicating an organized breeding industry operating within the city. And this discovery raises extraordinary questions about how tropical birds were kept alive in a semi-desert environment, how breeding populations were maintained, and how temperature, shelter, nutrition, and water requirements were managed, since modern avian specialists know that successful breeding programs require detailed understanding of animal behavior and environmental conditions, and even small mistakes can disrupt reproduction. Yet ancient residents of Casas Grandes appear to have sustained large numbers of birds over extended periods, suggesting something far beyond occasional exotic pets. And many researchers believe scarlet macaw feathers played important ceremonial and economic roles throughout the American Southwest, where their bright red plumage was highly valued and may have functioned as a prestige commodity within long-distance trade networks. So, if this interpretation is correct, Casas Grandes may have operated one of the most sophisticated animal production systems in pre-Columbian North America, with remarkable implications, as a city located in a desert may have mastered aspects of tropical animal husbandry that remain difficult to reconstruct today, and no complete explanation currently exists. The macaw mystery connects directly to another unresolved question regarding how Casas Grandes became a major trade hub, as artifacts recovered from the site include marine shells from distant coastlines, copper objects from western Mexico, exotic minerals, ceremonial goods, and materials originating hundreds or even thousands of kilometers away, revealing participation in an enormous exchange network stretching across much of the American Southwest and northern Mexico. The logistical challenge was immense because there were no horses, no wheeled transport systems used for freight, and no mechanized infrastructure, meaning goods moved primarily through human effort, yet valuable materials consistently reached the city, leading researchers to continue debating whether Casas Grandes functioned as a central redistribution hub, a cultural crossroads, or a political center controlling regional commerce. And whatever the answer, the scale of exchange demonstrates organizational capabilities far beyond earlier assumptions. Around the 15th century, Casas Grandes was abandoned, and the reasons remain uncertain, as evidence points towards several possibilities including prolonged drought, environmental stress, social conflict, economic disruption, changing trade routes, or combinations of multiple factors. While some structures show signs of burning and others appear to have been deserted, yet no single explanation fully accounts for all available evidence. And this uncertainty mirrors a broader pattern found across archaeological history, where many ancient societies achieved extraordinary levels of sophistication before undergoing transformations that remain only partially understood, placing Casas Grandes firmly within that category. In the ruins of Aphrodisias in southwestern Turkey, there stands a structure that feels less like architecture and more like a controlled system. The Sebastion of Aphrodisias, built in the 1st century CE to honor the emperors of the Roman Empire, is not simply a ceremonial space. It is a corridor nearly 90 meters long, bordered by multi-story walls that once carried more than 80 large marble reliefs. These reliefs were not randomly placed. They were arranged in a strict visual sequence, guiding the observer through mythology, conquest, and imperial authority. The central mystery is not the imagery itself, but the precision behind it. How material, structure, and narrative appear engineered with a level of consistency that challenges what we assume about ancient technical capability. The Sebastion did not reveal itself as a complete monument. Its modern story began in fragments during the 20th century, when archaeologists, most notably Keenan T., Erim began systematic excavations in the 1960s. What they encountered was not an intact structure, but a field of scattered components, collapsed walls, reused marble blocks, and relief panels embedded into later constructions. At first, these fragments seemed disconnected, but as excavation seasons progressed, patterns began to emerge. Relief panels were identified not as isolated artworks, but as parts of a larger composition. By the 1980s, enough material had been catalogued to reconstruct significant portions of the facade. Archaeologists determined that the corridor had been flanked by 2 parallel walls, each rising in multiple tiers, with sculptural panels arranged in vertical registers. Each register carried a different category of imagery gods, heroes, emperors, and personified regions of the empire. This was not decoration. It was sequencing. The site gradually revealed itself as a dismantled narrative architecture, one that had been designed to deliver information in a controlled visual order. In this sense, the discovery was not just physical, but conceptual. The realization that the Sebastion functioned as a structured system rather than a static monument. Aphrodisias was famous in antiquity for its marble quarries, producing a fine-grained calcite stone with crystal sizes, often below 1 millimeter and relatively low impurity levels. Such material allows for high-detail carving, but the Sebastion pushes this advantage into a range that raises deeper technical questions. Detailed measurements of surviving reliefs show extremely controlled carving depths. In many panels, transitions between foreground figures and background surfaces occur within just a few millimeters, creating smooth gradients of shadow that resemble modern bas-relief techniques. Anatomical features, muscle tension, facial symmetry, even the layering of fabric are executed with remarkable consistency across multiple panels. Scientific analysis of symmetry indicates deviations, often within 1 to 2 millimeters across bilateral features of faces. For hand-carved stone, repeated at scale, this level of accuracy is difficult to explain without some form of guiding system. Roman sculptors are known to have used iron chisels, claw chisels, and abrasives such as emery, but these tools alone do not fully account for the uniformity observed. Microscopic studies of tool marks reveal another anomaly. Surface finishing appears to follow consistent, multi-stage processes. Certain areas are deliberately left matte, while others are polished to higher reflectivity. This suggests that artisans were not only carving forms but also engineering how light would interact with different textures. The result is a controlled visual effect, one that changes depending on viewing angle and illumination. When compared with other Roman achievements such as the structural precision of the Pantheon or the realism of imperial portrait sculpture, the Sebastian stands out for the density of fine detail per surface area. It is not simply well made, it is consistently precise. Several hypotheses attempt to explain this. One suggests the use of early pointing devices, mechanical systems, for transferring proportions from a model to stone. While these are documented in later periods, direct evidence for their use at this scale in the 1st century is scarce. Another theory proposes a highly organized workshop system, where different artisans specialized in stages such as rough cutting, detailing, and finishing, all guided by strict proportional templates. Yet even these explanations leave gaps. The consistency across dozens of panels, potentially produced over long periods, suggests not only skill but process control. The marble was not just carved, it was processed in a way that approaches repeatability, a concept closer to engineering than traditional craftsmanship. Beyond the material itself, the Sebastian reveals a second layer of precision: standardization in imagery. Figures across different panels share consistent proportions, similar poses, and recurring anatomical structures. Heads align with comparable ratios to body height. Limbs follow repeated geometric relationships, and stances are variations of a limited set of base forms. This suggests the use of templates or canonical models. Inscriptions and stylistic differences indicate that multiple sculptors work simultaneously, yet the final output remains cohesive. This implies centralized planning, a design system that ensured consistency across independent contributions. Such standardization was not unknown in the Roman Empire. It can be seen in coin production, military equipment, and architectural modules. However, applying it to narrative relief sculpture at this scale is unusual. Here, standardization is used not to simplify production, but to maintain a unified visual language across a complex ideological program. The result is a form of controlled variation. Each panel is unique, yet all belong to a single system. This balance between repetition and difference is a hallmark of structured design. The Sebastian is not only about what is carved, but how it is experienced. The corridor's proportions, long, narrow, and enclosed, create a directional flow that guides movement forward. Visitors would not wander randomly. They would be led through a controlled path. The vertical arrangement of reliefs adds another layer. Lower panels are easily visible, while upper tiers require the viewer to look upward, shifting attention across multiple levels. This creates a structured viewing sequence, forcing engagement with the imagery in a specific order. Lighting plays a critical role. Studies suggest that sunlight would have entered the corridor at particular angles throughout the day, selectively illuminating certain panels while leaving others in shadow. This dynamic interaction between light and relief enhances depth perception and emphasizes different parts of the narrative over time. Such coordination implies intentional design. While Roman architects understood orientation and illumination, the level of integration here suggests something more deliberate, an early form of perceptual engineering. The space does not simply contain images, it controls how those images are perceived. Do you think the Sebastian is simply the peak of ancient craftsmanship, or evidence of a technical system we still don't fully understand? Share your thoughts in the comments below. On the shifting edge of the Danube, near modern Archaeological, a Roman fortress once rose on ground that behaves less like land and more like a slow-moving system. Fine sediments, seasonal flooding, lateral river migration — this is not where long-term military infrastructure is supposed to survive. And yet, for centuries, Novia Dunum did not just exist, it held. What makes Novia Dunum unusual is not its identity as a Roman stronghold, but the quiet contradiction embedded in its foundation. Because everything we understand about ancient engineering suggests that structures of this scale — defensive walls several meters thick, harbour installations, storage complexes — require predictability beneath them. Stability, resistance. The Danube floodplain offers none of these, and that is where the anomaly begins. Geologically, the lower Danube basin is composed largely of alluvial deposits, layers of sand, silt, and clay laid down over thousands of years. These materials compress under load, shift with water saturation, and erode under lateral flow. Modern civil engineering treats such environments as high-risk zones. Large constructions require deep piling, soil stabilization, or relocation to firmer ground. Roman engineers were not unaware of this. In places like Colosseum or Pont du Gard, foundations were carefully adapted to terrain, often using layered stone, pozzolanic concrete, and drainage systems to control moisture and load distribution. Even riverine constructions, such as bridges along the Rhine, were anchored into more stable substrates. But at Novia Dunum, the archaeological record suggests something different. Excavations indicate that massive defensive walls, likely exceeding 2 to 3 meters in thickness, were erected directly on floodplain soil. No clear evidence of deep foundational pilings has been consistently identified. No extensive substructures comparable to those used in other Roman sites appear in the surviving data. And yet, structural collapse does not dominate the site's history. This raises a contradiction. If the soil behaves as expected, the fortress should have experienced progressive subsidence, cracking, and eventual structural failure within decades, perhaps a century at most. Instead, Novia Dunum remained operational from at least the 1st century CE into the Byzantine period, spanning several hundred years. One possible explanation is that the Romans employed ground preparation techniques that are either not preserved or not yet recognized. Compacted gravel layers, timber mats, or drainage channels could have redistributed load and reduced water retention. However, the scale required to stabilize an entire fortress of this size would have been immense, and the archaeological footprint of such interventions remains incomplete. Another possibility is more unsettling: that the environmental conditions of the Danube at the time of construction were significantly different. River channels migrate over centuries. Sediment deposition patterns shift. What is unstable today may have been relatively firm in the past. Yet paleo-environmental reconstructions suggest that while local variations existed, the broader floodplain dynamics were already active during the Roman era. So the question remains unresolved. Not how the fortress was built, but how it endured. Most long-lived settlements tell a story of gradual adaptation. Materials improve, techniques evolve, repairs become visible as distinct phases. At sites like Pompeii, stratigraphy reveals a clear sequence, each layer reflecting a step in technological or cultural change. Noviodunum complicates this expectation. Here, layers exist, but the transitions between them do not always follow a linear progression. In some sectors, finely cut stonework appears abruptly, adjacent to more irregular masonry. Certain walls exhibit construction precision that aligns with advanced Roman techniques, while nearby structures suggest more expedient or localized methods. The inconsistency is not total, but it is persistent enough to disrupt the assumption of continuous development. This opens multiple interpretations. The site may have hosted different construction teams with varying levels of expertise. Periods of rapid rebuilding, perhaps after damage or strategic shifts, could have introduced abrupt changes in quality. Alternatively, materials may have been reused, creating a patchwork of styles that masks an underlying continuity. Yet even these explanations do not fully resolve the pattern, because the distribution of these variations does not always align neatly with known historical phases. It is as if the technological narrative of the site has been partially erased, leaving behind fragments that no longer connect in a straightforward way. Noviodunum was more than a fortress. It functioned as a naval base for the Roman fleet on the Danube, the Classis Flavia Moesica. This implies the presence of docking facilities, storage areas, and access points designed for repeated use. However, when modern researchers examine the relationship between the site and the river, inconsistencies emerge. Some structures associated with the harbour appear positioned in zones where current flow is strong, increasing the difficulty of stable docking. Other areas that would be more suitable for anchorage show less architectural investment. Additionally, geomorphological studies indicate that the Danube's course in this region has shifted over time, altering the relationship between land and water. This leads to a critical uncertainty. Were these structures optimally placed at the time of construction, only to be rendered impractical by later environmental change? Or were they designed according to criteria that differ from our assumptions about Roman naval logistics? Comparisons with other river ports, such as those along the Rhine or in the eastern provinces, generally show alignment between infrastructure and hydrodynamic conditions. Noviodunum does not always conform to this pattern, and without a precise reconstruction of the ancient river channel, the original logic of the harbour remains partially obscured. Many Roman fortresses end with clarity. Destruction layers, burn marks, weapon deposits, evidence of conflict that explains their abandonment. Others decline gradually but leave textual or material records that trace their final phases. Noviodunum offers neither in a complete form. Its occupation extends into the Byzantine period, suggesting continued strategic relevance. Yet at some point, activity diminishes, and the site fades from prominence. There is no single catastrophic layer that marks its end. No definitive record of conquest or deliberate destruction tied directly to its final abandonment. Instead, it appears to have been left behind. This is particularly difficult to reconcile with its location. Positioned along a major artery of movement and trade, controlling access along the Danube frontier, Noviodunum should have retained value. Even if damaged, such a site would typically be repaired, repurposed, or replaced. Unless the conditions that made it valuable changed in ways that are not fully captured in the surviving record. What makes Noviodunum unusual is not a single mystery, but the accumulation of mismatches. A fortress built on unstable ground yet enduring for centuries, structural layers without a clear progression, a harbour that does not fully align with its environment, and an ending with no definitive explanation. More importantly, the data surrounding it is incomplete. Compared to similar Roman sites, Noviodunum lacks sufficient records to fully explain how it was built or operated. As a result, it exists in a state between known and understood. Not an impossible technology, but a case where the frameworks we use to interpret history begin to diverge. Each piece makes sense on its own, yet the full picture remains unresolved. And perhaps that is the deepest mystery, not that it cannot be explained, but that it almost fits and then doesn't. So what do you think? Was Noviodunum simply misunderstood? Or are we missing a piece of history that was never recorded? Let me know your thoughts in the comments below. Along the Red Sea escarpment, on a wind-exposed plateau more than 2,600 meters above sea level, Quahito at first appears to be a modest cluster of ruins. But beneath that simplicity lies a contradiction. Here, in an environment defined by water scarcity, thermal stress and erosion, ancient builders created a settlement that not only endured, but operated with a level of engineering logic comparable to far more advanced civilizations. The most unsettling mystery is not what was built, but how every part of the system seems to solve problems with an efficiency that should not have been possible with the tools and knowledge of its time. Although local populations had long known of the ruins, Quahito entered formal archaeological awareness in the early 20th century, during surveys of the Eritrean highlands conducted under Italian colonial administration. Subsequent expeditions throughout the 20th century mapped the plateau, revealing an extensive network of terraces, reservoirs, temples, and domestic structures spread across several square kilometers. Artifacts recovered, including inscriptions in the South Arabian script and architectural parallels, linked the site to the Kingdom of Aksum, a major trading power between roughly the 1st and 7th centuries CE. Yet even with this cultural attribution, the technological coherence of Quahito remained unexplained. Excavations produced fragments of a civilization but not the blueprint behind it. The defining constraint of Quahito is water. The plateau lacks any permanent river, and modern rainfall averages between approximately 300 and 500 millimeters annually, highly seasonal and unreliable. Yet archaeological evidence indicates a settlement capable of supporting a substantial population. At the center of this paradox stands the Saphira Dam, an ancient structure designed to capture and store runoff from rare rain events. Combined with rock-cut cisterns and channel systems, the plateau forms an integrated hydraulic network. Estimates suggest that even a modest reservoir capacity of several thousand cubic meters could sustain hundreds, possibly thousands of inhabitants if managed efficiently. This implies not only construction capability, but hydrological foresight, understanding runoff patterns, evaporation rates, and storage efficiency. Comparatively, Roman cistern systems such as those in North Africa relied on similar principles, but were typically supported by formalized surveying tools, standardized measurements, and written engineering traditions. At Quahito, no such documentation has been found. The system exists, functions logically, yet lacks an identifiable knowledge framework. The architecture of Quahito is dominated by dry stone masonry, carefully shaped blocks assembled without mortar. This technique is widespread in ancient construction, from Mediterranean terraces to Andean walls. However, the execution here introduces a critical anomaly. Stone blocks are fitted with remarkable precision, reducing voids and enhancing structural stability. In many locations, walls remain standing after nearly 2,000 years of exposure. The precision suggests controlled shaping, yet there is limited evidence of advanced metal tools typically associated with such work. From an engineering standpoint, such tight-fitting construction reduces internal stress distribution and increases resistance to lateral forces, including wind and minor seismic activity. But this raises a question of intent. In a resource-limited environment, why invest labor into achieving a level of precision beyond what is structurally necessary? This pattern echoes other ancient sites such as Inca stonework at Machu Picchu, where precision appears to exceed immediate functional requirements. In both cases, the construction implies a deeper understanding of material behavior than the archaeological record clearly supports. The most difficult mystery to reconcile is not structural design, but material survival. High-altitude plateau environments impose extreme stress on stone construction. Daily temperature fluctuations can exceed 20 degrees Celsius, producing cycles of thermal expansion and contraction. Over time, this leads to microfracturing, displacement, and eventual collapse, particularly in dry masonry systems lacking binding agents. Wind erosion further accelerates degradation, especially in exposed terrains such as Kuhaito. Under such conditions, many ancient dry stone structures elsewhere show significant collapse within centuries. Yet at Kuhaito, numerous walls and terraces remain partially intact after nearly 2 millennia. Stones show limited displacement. Structural lines remain coherent. In some cases, surface textures suggest deliberate shaping or finishing that may influence weather resistance. From a material science perspective, durability at this scale implies one or more of the following: careful selection of lithology, choosing stone types with low porosity and high Mcalmet to thermal stress. Optimization of block geometry, minimizing stress concentrations and improving load distribution. Possible surface treatment, whether through polishing, heat exposure, or other unknown methods that alter erosion rates. The absence of binding material makes this even more striking. Stability emerges purely from geometry, mass, and friction. When compared to other ancient sites exposed to similar climates such as dry stone settlements in the Levant or North Africa, Kuhaito's preservation appears disproportionate. It does not simply survive. It persists beyond what environmental models would predict. Beyond individual structures, the plateau reveals signs of coordinated planning. Terraces are aligned to maximize land use and possibly control runoff. Pathways connect elevated and lower zones efficiently. Architectural clusters suggest zoning, domestic, ceremonial, and possibly administrative. Such organization implies a systemic approach to settlement design. Yet, unlike Roman or Mesopotamian contexts, there is no surviving body of written engineering instructions, measurement systems, or architectural treatises associated with the site. This absence creates a paradox. The physical evidence indicates planning. The historical record does not preserve the process. Kuhaito is often interpreted as part of the broader Aksumite world, a civilization known for trade networks extending across the Red Sea and into the Mediterranean. However, even within that context, the plateau stands apart. Its solutions are highly localized, tailored to a specific environmental constraint. Its engineering is efficient, but not visibly derived from known traditions. And most importantly, its knowledge system, whatever produced it, has left almost no trace. There is no gradual progression visible in the archaeological layers that leads clearly to this level of integration. Instead, the system appears already functional, already optimized. So how did a system this coherent exist, without leaving behind the knowledge that made it possible? What do you think explains Kuhaito's engineering, lost knowledge, overlooked science, or something else entirely? Share your thoughts in the comments below. Civilizations collapse in patterns. Systems fail, trade disappears, knowledge fragments. Yet in the aftermath of the Late Bronze Age collapse, when the Mycenaean world disintegrated around 1200 BCE, one small settlement on the island of Euboea did not follow the script. Lefkandi did not simply survive. It operated with a level of structural planning, material understanding, and long-distance connectivity that should not have been possible in a so-called Dark Age. Systematic excavations at Lefkandi began in the 1960s, led by archaeologists including Mervyn Popham and Nicholas Coldstream. What initially appeared to be a modest settlement quickly revealed stratified occupation layers, spanning the transition from the Late Bronze Age into the Early Iron Age. The defining moment came with the excavation of the Toumba Cemetery, where an unusually large structure later termed the Haroun was uncovered. Its scale, burial contents, and construction method immediately contradicting the prevailing model of cultural decline in post-Mycenaean Greece. The Toumba building measures approximately 50 meters in length and 10 meters in width, a scale that far exceeds most domestic structures in early Iron Age Greece, which rarely surpass 10 to 15 meters. Even Mycenaean megarons, such as those at Mycenae, while monumental, were constructed in stone and tied to centralized palace economies. At Lefkandi, however, the structure was built primarily from perishable materials, timber posts, mud brick walls, and a thatched roof. Yet its layout reveals a level of architectural planning defined by evenly spaced load-bearing columns, symmetrical organization along an elongated axis, and curved apsidal ends that require controlled geometric execution. From an engineering perspective, maintaining structural stability over a 50-meter span using timber and mud brick demands an understanding of weight distribution and lateral forces, and modern reconstructions suggest that post-placement would need to remain within tolerances of only a few centimeters to prevent progressive failure. The paradox is immediate. During the Greek Dark Age, literacy disappears, monumental stone construction declines, and regional connectivity fragments. Yet, no evidence exists of iterative architectural development leading to this structure. No prototypes, no transitional forms, only a design that appears fully realized. Euboea presents a coastal Mediterranean environment marked by seasonal humidity, salt exposure, and localized soil instability, conditions under which mud brick structures typically degrade within decades without continuous maintenance, while untreated timber is highly susceptible to rot and biological damage. Yet the archaeological footprint of the Toumba structure remains sufficiently intact to allow full reconstruction of its ground plan, with evenly spaced post holes, coherent wall lines, and subsidence patterns that indicate controlled structural decay rather than chaotic collapse. This suggests that the builders possessed a working understanding of soil compaction for stable foundations, selective use of timber species with higher resistance to decay, and drainage strategies that prevented water accumulation at structural bases. Comparable mud brick settlements in the Near East, such as Çatalhöyük, required constant rebuilding cycles to maintain structural integrity, whereas at Lefkandi, the building appears to have remained functional long enough to serve a ceremonial role before its intentional burial, raising a deeper question. Not whether such technical knowledge existed, but why it appears here without any visible transmission pathway or developmental lineage. Inside the Toumba structure, archaeologists uncovered a burial assemblage that merges multiple ritual traditions into a single, highly coordinated event. A male individual cremated and placed within a bronze amphora imported from Cyprus. A female individual buried intact and adorned with intricate gold jewelry, and the remains of 4 horses carefully arranged and sacrificed nearby. Each element carries distinct cultural implications, cremation becoming dominant in later Greek practice, but remaining rare in earlier Mycenaean elite contexts, inhumation reflecting older traditions, and horse sacrifice representing elite status yet requiring substantial economic resources. Maintaining and sacrificing horses in the early Iron Age implies access to grazing systems, breeding knowledge, and organized labor, while the presence of a Cypriot bronze vessel demonstrates ongoing trade connections across the eastern Mediterranean, spanning distances of several hundred kilometers. In contrast, most contemporaneous sites across mainland Greece show reduced material complexity, limited imports, and simplified burial customs. Lefkandi does not conform to this pattern. Instead, it integrates multiple cultural systems into a unified ritual framework, suggesting deliberate synthesis rather than cultural fragmentation. The late Bronze Age collapse disrupted major trade systems linking the Aegean, Anatolia, and the Levant, with archaeological evidence from sites such as Ugarit indicating sudden destruction around 1200 BCE and the disappearance of administrative systems like Linear B writing. Yet Lefkandi yields imported goods from Cyprus, the Near East, and possibly Egypt, pointing to the survival of maritime exchange networks in some form. Even a minimal network would require navigational capabilities across open sea distances exceeding 100 kilometers, shipbuilding techniques capable of repeated voyages, and social coordination mechanisms to sustain exchange. Rather than complete collapse, the evidence suggests fragmentation into smaller decentralized systems, with Lefkandi functioning as a node within this reduced but persistent network. If such connectivity continued beyond the visible collapse of major civilizations, then the traditional concept of a total economic breakdown during the Greek Dark Age becomes increasingly difficult to sustain. The concentration of gold ornaments, imported ceramics, and high-value materials at Lefkandi indicates the presence of an elite class capable of controlling resources and organizing labor at a level inconsistent with models of societal regression. While post-collapse societies are generally expected to exhibit reduced hierarchy and dispersed wealth, Lefkandi demonstrates centralized authority, access to surplus beyond subsistence needs, and continuity in symbolic and ritual expression. Compared to other settlements across mainland Greece during the same period, many of which show smaller population sizes, limited artifact diversity, and simplified construction, Lefkandi emerges not merely as an anomaly, but as a direct contradiction of the expected trajectory of decline. By the 9th century BCE, Lefkandi enters a phase of decline and is eventually abandoned without clear evidence of violent destruction, large-scale fire, or catastrophic environmental change. There is no direct continuation into a larger urban centre, and perhaps more significantly, no architectural lineage linking the Tumba structure to later Greek temple forms, which adopt entirely different proportions and construction systems. The knowledge embedded in the design of the Haroun does not visibly transfer into subsequent architectural traditions. It appears within the archaeological record, persists for a limited period, and then vanishes without continuity. What do you think Lefkandi really represents? A rare anomaly in a broken world, or a surviving fragment of a hidden network we have yet to fully understand? High in the Lake Titicaca basin of western Bolivia, near the core territory of the Tiwanaku civilization, lies a settlement that should not exist in the form we see it today. Lucaramata does not overwhelm with monumental gates or towering stone icons. Instead, it unsettles for a different reason, because it looks incomplete yet strangely intentional, as if frozen mid-thought. Archaeological surveys indicate continuous occupation from roughly 1500 BCE to 1000 CE, spanning nearly 2.5 millennia, a duration that places Lucaramata among the longest continuously inhabited sites in the Andean highlands. But what truly sets it apart is that many structural patterns, agricultural systems, and spatial organizations seen here appear before they are fully realized at Tiwanaku itself. suggesting a developmental sequence that runs counter to expectations. This raises a rarely asked question in archaeology. What if Lucarmata was not a peripheral settlement, but a prototype, a place where systems were tested, refined, and sometimes abandoned long before they shaped one of the most influential civilizations in pre-Columbian South America? Unlike many ancient cities that vanish beneath jungle or desert, Lucarmata was never truly lost, as its remains persisted in the landscape and blended into agricultural zones surrounding Lake Titicaca, quietly existing without dramatic rediscovery. Systematic archaeological investigation began in the mid-20th century, with major work during the 1970s and 1980s led by researchers such as Alan Colata, who revealed that Lucarmata was not a single-phase settlement but a layered record of transformation, where architecture evolved gradually, agricultural systems expanded and contracted, and social organizations shifted across centuries. Unlike Tiwanaku, which presents a relatively unified urban vision with standardized monumental planning, Lucarmata reads more like a timeline of experimentation, a site where ideas were continuously tested rather than finalized, offering archaeologists a rare longitudinal view into how a complex society may have developed its systems over time. Excavations show that Lucarmata developed gradually without the sudden architectural standardization observed at Tiwanaku between roughly 500 and 800 CE, and instead its construction phases reveal variation, where different building techniques coexist, some refined while others appear abandoned mid-process, suggesting an iterative approach rather than a finalized plan. In Tiwanaku, stone blocks are often precisely cut and fitted with minimal mortar, reflecting a mature engineering tradition, whereas at Lucarmata, archaeologists encounter walls with inconsistent alignment, foundations indicating redesign during construction, and transitions between crude and advanced masonry within the same structural contexts, patterns that are difficult to interpret as simple inefficiency. Comparable developmental layering has been observed at sites such as Çatalhöyük, where architecture reflects social adaptation over time, yet Lucarmata differs in both scale and duration, persisting for centuries under increasingly complex environmental and social conditions, implying that what appears incomplete may actually represent a phase of continuous experimentation. This leads to an unsettling implication that Lucarmata may not be a less advanced site at all, but rather a place where advancement itself was being defined through repeated trial, error, and refinement. Surrounding Lucarmata lies one of the most sophisticated ancient agricultural systems ever documented, the raised field system known locally as Waru Waru, which operates in an environment that by conventional standards should be agriculturally unstable. Given that the altitude exceeds 3,800 meters above sea level, nighttime temperatures frequently fall below freezing, frost events occur unpredictably, and soil fertility is naturally limited without intervention. Despite these constraints, the system achieves remarkable efficiency by constructing elevated planting platforms separated by water-filled canals, where solar radiation heats the water during the day, and that stored heat is slowly released at night, creating a localized thermal buffer that can raise surrounding air temperatures by approximately 1 to 2 degrees Celsius, a seemingly small margin that is nevertheless sufficient to prevent frost damage to crops. Modern experimental reconstructions in the Lake Titicaca basin during the 1980s demonstrated that such systems could produce yields 2 to 3 times higher than conventional high-altitude farming under comparable conditions, indicating that this was not an accidental adaptation, but a form of engineered microclimate control. The implications are profound because implementing such a system requires an implicit understanding of thermal inertia, heat exchange, hydrology, and long-term climatic observation, yet the Tiwanaku culture left no written language describing these processes. When compared to irrigation systems in Mesopotamia, which relied primarily on river flooding cycles and canal distribution, or even Roman agricultural engineering, which emphasized water transport rather than microclimate manipulation. The Lucarmata system appears conceptually closer to modern agroengineering practices than to its ancient counterparts. This raises a difficult question regarding the nature of knowledge transmission in such societies, because while one hypothesis suggests gradual accumulation of empirical knowledge across generations, and another proposes distributed knowledge systems embedded within communal practice, neither fully accounts for the precision and scalability observed across the landscape, leaving open the possibility that the knowledge was more systematic than currently assumed, but encoded in forms that have not survived or are not yet recognized by modern archaeology. Large-scale agricultural systems typically imply centralized authority structures capable of organizing labor, managing resources, and enforcing coordination, a pattern evident in civilizations ranging from Mesopotamia to ancient Egypt. Yet Lucarmata does not conform to this expectation, as there is no clear evidence of monumental palaces, elite tombs filled with wealth, or dominant religious complexes exerting visible control over the landscape. Instead, the archaeological record suggests a relatively uniform distribution of structures, pointing toward a more decentralized or possibly egalitarian social organization, which directly challenges a foundational assumption in archaeology that complexity must be accompanied by visible hierarchy. This contradiction raises the possibility that Lucarmata operated under a different model of social organization, perhaps one in which knowledge systems rather than political authority structured society, or alternatively that the markers of hierarchy were constructed from perishable materials that have not survived, or encoded in symbolic systems that remain undeciphered. In either case, the absence of visible power structures does not indicate simplicity, but rather a form of complexity that does not align with traditional models. By around 1000 CE, both Lucarmata and the broader Tiwanaku system entered a period of decline, and paleoclimate data derived from ice cores and lake sediment analysis indicate a prolonged drought between approximately 900 and 1100 CE, which would have reduced water availability and placed stress on agricultural production. Yet this explanation remains incomplete because raised field agriculture is inherently resilient, designed to buffer frost, regulate moisture, and stabilize yields even under fluctuating environmental conditions. If any agricultural system should have endured climatic stress, it would have been this one, and yet it was ultimately abandoned, with no widespread evidence of warfare, no clear destruction layers, and no signs of sudden catastrophe, only a gradual cessation of activity. This pattern suggests a more complex collapse mechanism, possibly involving the breakdown of social coordination, the loss of specialized knowledge required to maintain the system, or a threshold effect in which environmental stress accumulates until even resilient systems fail abruptly. In modern systems theory, such a process is described as nonlinear collapse, where stability persists for long periods before giving way to rapid failure, and Lucarmata may represent one of the earliest empirical examples of such dynamics in human history. What do you think? Was Lucarmata a deliberate testing ground for one of South America's greatest civilizations? Or are we projecting modern concepts of experimentation onto a past that operated under entirely different principles? Humans learned to build cities gradually. At least, that is what the historical model suggests. Villages became towns, towns became fortified centers, and only after thousands of years did complex urban planning emerge. But at unit site, this sequence appears to collapse. Buried beneath layers of earth in southern Bulgaria lies a settlement dated to approximately the 6th millennium BCE. Yet it displays structural decisions that resemble far later civilizations. Defensive walls several meters thick, repeated reconstruction phases, and material stability across millennia, all appearing at a time when most of Europe had not yet developed large-scale architecture. The anomaly is not that unitsite exists. The anomaly is that it exists too early, too complete, and too stable. The site of unitsite was first identified in the 20th century during systematic archaeological surveys of the Thracian plain. Excavations intensified in the 1970s and continued into the 21st century, revealing a tell settlement, a mound formed by continuous human occupation over thousands of years. Stratigraphic analysis demonstrated that the deepest layers date back more than 7,000 years, placing unitsite among the earliest large-scale settlements in Europe. Each excavation phase revealed something unexpected. Beneath later Bronze Age and Iron Age layers, archaeologists uncovered a Chalcolithic settlement with fortifications, including walls estimated at 3 to 4 meters thick. Radiocarbon dating confirmed their antiquity, aligning them with a period when metallurgy was minimal and construction tools were still predominantly stone-based. Yet the structural logic of these walls suggested planning, reinforcement, and long-term durability. This is where unitsite becomes genuinely difficult to explain. The environmental conditions of the region are not favorable for long-term preservation of primitive materials. The Thracian plain experiences seasonal temperature variation exceeding 30 degrees Celsius, along with periods of heavy rainfall and fluctuating humidity. The soil composition is largely alluvial, rich but structurally unstable, prone to erosion and water infiltration. Under such conditions, construction based on rammed earth, timber, and unprocessed stone should degrade rapidly, often within decades or, at most, a few centuries. And yet, at unitsite, structural layers have persisted for millennia. Microscopic analysis of soil samples taken from the fortification walls shows a level of compaction that suggests intentional density control, not random accumulation. Grain alignment and compression patterns indicate repeated mechanical action, implying that builders deliberately optimized the internal structure of the material. The layering pattern, alternating compacted earth with inclusions of stone and organic material, resembles early forms of composite engineering. In modern terms, such layering can improve load distribution, reduce stress concentration, and increase resistance to cracking. Similar in principle to how reinforced concrete distributes internal forces. But here lies the paradox. There is no evidence that the builders possessed theoretical knowledge of material science. There are no written records, no instruments capable of measuring pressure or density, and no established tradition of large-scale engineering at that time in Europe. The knowledge appears functional, precise, and effective, yet completely undocumented. Comparisons make the anomaly clearer. Rammed earth structures from later historical periods, including fortifications of the Han Dynasty or medieval European earthworks, often show significant degradation after centuries. Many require restoration, reinforcement, or collapse entirely under prolonged environmental stress. Even when constructed with more advanced tools and organized labor, their longevity is limited by environmental exposure. Yet, unitsite's core structures remain stable enough to be identified thousands of years later, preserving both form and stratigraphic clarity. Even more puzzling are traces of thermal alteration. Some sections of the walls show signs of exposure to high temperatures, likely from destructive fires, yet instead of disintegrating, certain layers appear to have hardened, increasing their resistance. This effect resembles modern processes where controlled heating can alter the microstructure of clay, enhancing its compressive strength and durability. However, there is no clear evidence that such processes were intentionally applied, raising the possibility that either accidental conditions produced beneficial outcomes or that the builders possessed empirical knowledge of heat-based material transformation. What emerges is a possibility that challenges conventional narratives. The builders of UNAT site may have developed a form of empirical engineering, a system based not on formal theory but on iterative experimentation, observation, and refinement. Through repeated cycles of construction and reconstruction, they may have discovered methods of material stabilization that achieved results comparable to far later technologies. This would imply a feedback loop of knowledge accumulation operating without written transmission, a fragile system that could easily disappear if disrupted. But this leads to a deeper and more unsettling question. If such knowledge existed and proved effective, why does it not appear elsewhere in a continuous developmental chain? Why is it not clearly replicated, expanded, or transmitted into later European construction traditions? The walls of UNAT site are not merely thick, they are strategically constructed. Their layout suggests an understanding of defense, including layered barriers, controlled access points, and possibly elevated or reinforced sections designed to absorb or deflect force. This implies anticipation of organized conflict, not random threat. However, large-scale warfare in Europe during the Chalcolithic period is not well documented. Most settlements from this era show minimal defensive architecture, often consisting of simple boundaries or natural protection rather than engineered fortifications. By contrast, UNAT site appears to have been designed with threat mitigation in mind, as if its builders expected sustained external pressure or repeated confrontation. Evidence of destruction layers supports this interpretation. Burn patterns, collapsed wall segments, and directional debris distribution indicate that the settlement may have experienced violent attacks, possibly multiple times. The consistency of these patterns suggests organized events rather than isolated incidents. Reconstruction phases that follow show resilience and continuity, implying that the inhabitants rebuilt using similar structural logic, preserving their methods across generations. This introduces another anomaly. A fortified urban structure appears to exist before the widespread emergence of organized warfare in the region, suggesting either that conflict developed earlier than currently understood, or that UNAT site occupied a unique position within a network of interactions that remains largely invisible in the archaeological record. Perhaps the most unsettling aspect of UNAT site is not its sophistication, but its isolation in time. Archaeological sequences typically show gradual evolution. Techniques improve, spread, and diversify across regions. Innovations are adopted, modified, and integrated into broader cultural systems. Yet UNAT site does not clearly connect to a wider network of similar sites, exhibiting the same level of material and structural optimization. Its engineering features do not appear to propagate into later European construction traditions in any direct or traceable way. It is as if a system of knowledge briefly emerged, reached a functional peak, and then vanished. There are no direct descendants, no incremental improvements that can be clearly linked, no written transmission preserving the principles behind its construction methods. The continuity that defines most technological progress appears to be missing. In modern scientific terms, this resembles a discontinuous innovation event, a localized breakthrough that fails to integrate into a wider technological ecosystem. Such events are rare but documented in complex systems, where knowledge can emerge under specific conditions and disappear if those conditions are not maintained. However, their presence in deep prehistory complicates the linear model of human progress, suggesting that development may not always follow a predictable or cumulative path. What do you think happened at UNAT site? Was this the result of lost knowledge, experimental engineering, or something else entirely? Perched atop a flat-topped sandstone plateau in northern Ethiopia, the Debre Damo Monastery rises more than 15 meters above sheer vertical cliffs, cut off from the surrounding world in a way that seems almost deliberate. The only way up is by a leather rope lowered from above, a method that has remained unchanged for centuries and still defines access to the site today. According to historical tradition, the monastery was established in the 6th century CE by Abuna Aragawi, one of the 9 saints credited with spreading Christianity across the region. By the 19th century, European explorers and missionaries had already documented the same astonishing detail: a single rope hauled by monks, functioning as the only entry point to a fully developed religious complex. From the very beginning, Debre Damo presents a contradiction. Religious centers are typically designed to gather communities, to be seen, to be reached. This one was built to resist access to exist apart from it. And yet, for nearly 1,500 years, it has not only survived, but remained continuously inhabited. What makes Debre Damo truly mysterious is not just its isolation, but the unanswered question at its core. How is a permanent, complex structure constructed on a plateau that appears, even today, almost impossible to reach? Unlike pilgrimage centers such as Machu Picchu or fortified heights like Sigiriya, which incorporate engineered pathways, terraces, or carved staircases, Debre Damo offers no such accommodations. The vertical cliff surrounding the plateau is approximately 15 to 25 meters high, composed of weathered sandstone with minimal natural footholds. The rope ascent still used today requires upper body strength, coordination, and assistance from above. This raises a structural paradox. Archaeological patterns show that ancient builders typically optimized accessibility during construction phases, even if later restricted. At Debre Damo, however, there is no evidence of a former staircase, ramp, or carved access route that was later removed or destroyed. Geological surveys of similar sandstone escarpments indicate erosion rates on the order of fractions of a millimeter per year. Even over 1,000 years, such erosion would not fully erase a large-scale carved staircase without leaving detectable remnants. Yet none have been conclusively identified. The implication is unsettling. Either the builders constructed the site under conditions vastly different from today, or they employed temporary systems that left virtually no trace. The most persistent mystery surrounding Debre Damo lies in what might be called the plateau construction problem. The monastery complex includes stone walls, timber beams, roofing materials, and interior structures consistent with early Aksumite civilization architectural techniques. Some wooden beams, particularly the distinctive monkey head projections, are integral load-bearing elements. To construct even a modest building, several tons of material would have been required. Timber beams alone could weigh hundreds of kilograms each. Stone blocks, depending on size and density, would add significantly more. In other ancient sites, the logistics of vertical transport are well documented. At Machu Picchu, laborers used inclined ramps and switchback trails. At Sigiriya, engineers carved stairways directly into the rock face. Even in extreme environments, such as cliff dwellings in the American Southwest, access routes, however narrow, were always present. At Debre Damo, none of these solutions appear to exist. One hypothesis suggests the use of rope and pulley systems. However, for such systems to lift heavy loads consistently, they typically require stable anchor points, scaffolding, or mechanical advantage devices such as compound pulleys. There is no surviving evidence of such infrastructure on the plateau edges or below. Another theory proposes that construction occurred gradually, with materials lifted in smaller increments. While plausible, This introduces further complications. Repeated lifting of heavy materials over a vertical drop of 15 to 20 meters would require a coordinated labor force and durable rope technology. Experimental archaeology offers some insight. Tests with leather ropes and simple pulley systems suggest that lifting loads exceeding 100 kilograms vertically becomes increasingly difficult without advanced mechanical advantage. Yet the scale of construction at Debre Damo implies cumulative loads far beyond that threshold. A third possibility is that temporary wooden scaffolding or earthen ramps once existed and were later removed or eroded. However, sediment analysis around the base of the plateau has not revealed clear evidence of large-scale artificial ramp structures. The result is a logistical gap. There is no fully satisfactory explanation for how the necessary construction materials reached the plateau in the first place. Despite these uncertainties, the monastery has endured for over 14 centuries. The architectural style reflects Aksumite construction methods, characterized by alternating layers of stone and timber. This hybrid approach distributes stress and allows flexibility under environmental pressure. The projecting wooden beams often visible on exterior walls serve both structural and aesthetic functions. From an engineering perspective, such designs can enhance resilience. Modern studies of similar composite systems show improved resistance to cracking and seismic stress compared to rigid stone-only construction. However, Debre Damo's environment presents additional challenges. Elevated plateaus experience stronger wind exposure, temperature fluctuations, and accelerated weathering. Wood, in particular, is vulnerable to decay, insects, and moisture. Yet some original structural elements have survived for centuries, suggesting either exceptional material selection or maintenance practices that are not fully documented. Comparatively, many ancient structures built at ground level have suffered greater degradation. This raises another question. Did the isolation of the plateau, rather than hindering preservation, actually protect the site from human interference and environmental damage? Debre Damo is not merely a construction puzzle. It is a sustained human environment. The plateau spans a limited area, yet it has supported a monastic community for generations. Food, water, and supplies must be transported upward, while agricultural activity on the plateau itself is constrained. Anthropological comparisons with other isolated communities, such as monastic settlements on Mount Athos in Greece, reveal similarities in social structure, but significant differences in physical accessibility. Mount Athos, while restricted, remains reachable by land and sea. Debre Damo does not. This level of isolation suggests intentional design. The monastery functions as a controlled environment, limiting external contact and preserving religious traditions with minimal disruption. From a systems perspective, it resembles a self-regulating enclave where constraints reinforce continuity, but it also amplifies the original mystery. Juzo and Comte A. Few, why invest such effort to create a site that is inherently difficult to sustain? The founding legend of Abuna Aragawi describes his ascent aided by a giant serpent, a narrative that transforms an impossible climb into a divine act. While clearly symbolic, such stories often encode real challenges in mythological form. Across cultures, extraordinary engineering feats are frequently attributed to supernatural assistance when the underlying techniques are not understood or have been forgotten. In this sense, the legend may not explain the construction of Debre Damo, but it acknowledges its improbability. So, what do you think? Was this built using lost engineering methods, or are we still missing a crucial piece of the story? Share your thoughts in the comments below. discovery did not begin with a grand expedition, but with construction. In the late 20th century, urban expansion in the city of Jaén, southern Spain, exposed an unexpected pattern beneath the soil arcs of trenches, fragments of circular ditches, and repeated curvatures that did not align with any known medieval or Roman layout. Rescue excavations in the 1990s gradually revealed what satellite imagery would later confirm: a vast prehistoric complex composed of multiple concentric rings, extending across more than 100 hectares. Radiocarbon dating placed its primary occupation between roughly 3000 and 2500 BCE, positioning it firmly within the Copper Age. What initially appeared to be scattered features turned out to be part of a unified design, one that, even today, resists simple explanation. The first layer of mystery emerges from geometry. Marroquí's Bajos is not irregular, not organic, and not the result of slow, chaotic growth. It is structured. Archaeological mapping has identified at least 5 major concentric ditches, each separated by relatively consistent distances. In some sectors, spacing between rings varies by only a few meters across spans of several hundred meters, an error margin that suggests intentional measurement rather than approximation. For comparison, early Neolithic settlements across Europe, such as those associated with the linear band ceramic culture, typically display loosely organized layouts, expanding outward without strict geometric control. Even later fortified enclosures like causewayed camps in Britain show irregular interruptions rather than continuous symmetry. Marroquí's Bajos, by contrast, approaches the logic of planned radial design, something more commonly associated with much later urban experiments. This raises a fundamental technical question: how was such precision achieved? At a scale exceeding 1 kilometer in diameter, maintaining circular symmetry requires more than visual estimation. Modern reconstructions suggest that even a small angular deviation at the center would produce significant displacement at the perimeter. Without metal surveying instruments, standardized units, or written mathematical systems, the builders would have needed alternative methods, possibly rope-based measurement systems, fixed marquisee points, or repeated geometric iteration. Yet no intermediate stages, no trial layouts, no partial corrections have been identified. The system appears as if executed with prior conceptual clarity. If geometry defines the form, water defines the function, or at least complicates it. The concentric ditches are not merely empty boundaries. Sediment analysis indicates periodic water retention, with layers of silt suggesting controlled flooding events. Some sections display gradients that would allow directional flow, implying that water was not only present but managed. This introduces a level of hydraulic awareness that seems disproportionate to what is known about Copper Age communities in the Iberian Peninsula. In regions such as Mesopotamia, large-scale irrigation systems emerge in tandem with urbanization and agricultural intensification. Here, however, the scale of water management infrastructure appears to exceed the documented agricultural capacity of the settlement itself. Comparative estimates deepen the puzzle. To excavate even a single ditch of several meters width and depth, extending in a near-perfect circle over hundreds of meters, would require the removal of thousands of cubic meters of earth. Multiplied across multiple rings, the total labor investment reaches into the tens of thousands of man-hours. And yet, population estimates for the site based on dwelling remains suggest a community of perhaps a few thousand individuals at most. This implies either a highly organized labor system, seasonal workforce aggregation, or a longer construction timeline than currently assumed. But again, the archaeological record offers limited evidence for gradual accumulation. Instead, the structure reads as a coherent whole. Material behavior adds another layer of contradiction. The ditches and embankments were formed primarily from compacted earth, mixed with stones and organic inclusions. Under typical environmental conditions, seasonal rainfall, erosion, soil instability, such features should degrade rapidly, losing definition within centuries. However, portions of Marrakesh bargeos have retained identifiable stratification for over 4 millennia. Micromorphological studies of soil samples indicate deliberate compaction techniques, possibly involving moisture control during construction. This suggests that the builders possessed empirical knowledge of soil mechanics, how to increase density, reduce permeability, and stabilize structure over time. Such knowledge does not require formal science, but it does require repeated observation and transmission. Yet, as with other aspects of the site, there is little evidence of earlier, simpler precedents evolving into this level of execution. Function remains the most elusive variable. A defensive interpretation struggles under scrutiny. While ditches can serve as barriers, the openness of the system, the lack of consistent ramparts, and the sheer scale of enclosure reduce its efficiency as a fortification. A ceremonial interpretation introduces different challenges. The spatial organization is vast, far exceeding what is typically required for ritual gatherings, and lacks clear focal monuments such as temples or altars at the center. An agricultural model, centered on water control, must account for the mismatch between infrastructure scale and crop evidence. Each hypothesis explains part of the system, but none resolves it entirely. There is also the question of temporal behavior. Stratigraphic analysis indicates phases of use, modification, and eventual abandonment. However, the transition does not follow a clear pattern of decline. There is no widespread destruction layer, no consistent signs of conflict, and no abrupt environmental shift recorded in local paleoclimatic data that would fully justify abandonment. Instead, activity appears to diminish, features are gradually filled or repurposed, and the system dissolves into the landscape. In archaeological terms, this is not an ending marked by catastrophe, but by disengagement. When placed within a broader Eurasian context, Marrakesh Bajos becomes even more difficult to classify. Circular enclosures exist elsewhere, Neolithic rondels in Central Europe, for instance, but these are typically smaller, simpler, and more clearly ritual in function. Large-scale hydraulic systems appear in ancient Egypt and Mesopotamia, but they are embedded within literate, state-level societies. Here, in southern Iberia, a complex emerges that seems to borrow elements from both categories, geometry and water management, without fully belonging to either. One interpretation is that Marrakesh Bajos represents a peak of technical and organizational capability under conditions we do not yet understand. Another is that it reflects a lost knowledge system, or simply a longer developmental process that remains hidden from the archaeological record. Yet the anomaly remains. The site shows coordinated planning, controlled execution, and environmental adaptation at a scale that exceeds its context. It does not look like a gradual experiment, it looks complete. And that distinction matters, because if it was built as a finished idea, the real question is no longer how it was constructed, but where that idea came from. Toninar was not discovered in the dramatic, sudden way many ancient sites were. Instead, it emerged gradually from obscurity in the late 19th century, when explorers moving through the remote Ocosingo Valley in the highlands of Chiapas, southern Mexico, began documenting unusually massive stone terraces rising from the jungle floor. Early reports by researchers such as Desiree Charnay in the 1880s described a structure that did not resemble a conventional Maya city. What stood before them was not a spread of temples and plazas, but a single immense vertical formation. Later excavations throughout the 20th century, particularly those led by Mexico's National Institute of Anthropology and History, revealed the full scale of the site. A towering acropolis rising over 70 meters in height, composed of at least 7 superimposed terraces, making it one of the tallest structures in the entire Maya world. From the moment its layout became clear, Toninar presented a problem that has never been fully resolved. Unlike major centers such as Tikal or Palenque, which expand horizontally across wide ceremonial plazas, Toninar compresses its entire ceremonial and political core into a vertically stacked system. This is not a minor variation. It represents a complete departure from the spatial logic of Maya urbanism. The most immediate mystery is therefore structural. Why would a civilization known for expansive layouts choose instead to construct what is effectively a vertical city? The engineering implications alone are significant. Building upward at this scale in a tropical environment introduces challenges that horizontal cities largely avoid. Each terrace must support the cumulative weight of all structures above it, requiring precise load distribution across stone retaining walls. Archaeological analysis shows that these walls are not crude accumulations of rubble, but carefully constructed systems of fitted limestone blocks, some weighing hundreds of kilograms. The stability of the Acropolis over more than a millennium suggests a sophisticated understanding of pressure management and foundational support. Compared to other Maya constructions, where even modest pyramids required periodic reinforcement, Toninar's survival in a region with seasonal rainfall exceeding 2,000 millimeters per year is difficult to explain without assuming deliberate over-engineering. Even more striking is the issue of water control. In steep terraced environments, uncontrolled runoff typically leads to rapid erosion and structural collapse. Yet Toninar incorporates subtle but effective drainage solutions, channels carved into stone, angled surfaces that direct water away from critical joints, and layered platforms that reduce hydraulic pressure. When compared with sites like Copan, where erosion has significantly damaged architectural features despite less extreme verticality, Toninar appears disproportionately resilient. This raises a key question. Were its builders solving problems that did not yet exist, anticipating long-term environmental stress in a way that exceeds known Maya practices? The mystery deepens when examining how space is used within this vertical system. Movement through Toninar is not free or open. It is guided, constrained, and often deliberately disorienting. Staircases are steep and narrow, forcing single-direction flow. Terraces limit visibility, preventing large-scale observation of ceremonies from a single vantage point. This contrasts sharply with the open plazas of sites like Chichén Itzá, where architecture is designed to accommodate large audiences and communal viewing. At Toninar, spatial design appears to control not just movement but perception itself. This controlled environment becomes particularly significant when considering the site's massive ball court, one of the largest in Mesoamerica. Measuring over 100 meters in length, the court is embedded within the architectural framework rather than placed in an open civic space. Its elongated, enclosed design restricts both participation and observation, suggesting that the ball game here may have functioned differently than at other Maya centers. While traditionally interpreted as a ritual tied to cosmology and myth, at Toninar, it may have served as a form of controlled political performance, an event where outcomes and interpretations were tightly managed by elite authority. Archaeological evidence supports this interpretation. Toninar is renowned for its unusually explicit sculptural program, which emphasizes domination, captivity, and violence. Numerous monuments depict bound prisoners, decapitated figures, and victorious rulers standing over defeated enemies. These are not abstract representations of power. They are direct, almost confrontational statements. Inscriptions found at the site document repeated military conflicts, particularly with nearby Palenque, one of Toninar's primary rivals during the Classic period. Epigraphic studies indicate that Toninar may have captured and even executed high-ranking individuals from competing cities, reinforcing its political dominance through both action and imagery. What makes this significant is not merely the presence of violence, but its integration into the architecture itself. At Toninar, power is not confined to monuments or inscriptions, it is embedded into the physical experience of the site. As one ascends the terraces, the combination of steep elevation, restricted movement, and constant visual reminders of conquest creates an environment that may have been designed to influence psychological response. In this sense, the Acropolis functions less like a ceremonial center and more like a controlled spatial narrative, guiding individuals through a sequence of experiences that reinforce authority. Yet even this interpretation leaves critical questions unanswered. If Toninar was primarily a political instrument, why invest such extraordinary effort into vertical construction rather than more conventional displays of power? If it was defensive in nature, why does it lack many of the features typically associated with fortifications, such as perimeter walls or strategic lookout points? And if it was purely ceremonial, why does its engineering exceed the practical requirements of ritual use? Some researchers have proposed that Toninar represents a localized architectural experiment, a deviation driven by regional conditions or specific cultural priorities. Others suggest that its design reflects a symbolic attempt to replicate sacred mountains, aligning the city with cosmological beliefs about the layered structure of the universe. However, these explanations remain partial. Neither fully accounts for the combination of advanced engineering, spatial control, and aggressive iconography that defines the site. In comparative terms, Toninar occupies an unusual position within the Maya world. It is neither the largest nor the most artistically refined site, yet it demonstrates a level of structural ambition that rivals or exceeds more famous centers. Its verticality has few parallels, and its integration of architecture, engineering, and political messaging appears unusually cohesive. This combination suggests that Toninar was not simply following established traditions, but actively redefining them. Ultimately, the greatest mystery of Toninar may not lie in any single feature, but in the convergence of all its anomalies. It is a site where architectural form, environmental adaptation, and ideological expression intersect in ways that challenge existing models of Maya civilization. Despite decades of excavation and analysis, no single framework has been able to fully explain its design. Toninar stands, therefore, as more than an archaeological site. It is a question in stone, one that forces us to reconsider what ancient cities were meant to be and whether some of them were built not just to function, but to shape how people think, move, and perceive power itself.